DART, Double Asteroid Redirection Test. For decades, the threat of an asteroid colliding with Earth was treated as an apocalyptic scenario reserved for science fiction. But in 2022, NASA decided to test whether it would be possible to redirect a real space object from its trajectory. The DART mission had a defined target, Dimorphos, a small moon orbiting a larger asteroid called Didymos, about 11 million kilometers from Earth. The plan was simple in theory, but bold in practice: intentionally crash a high-speed spacecraft into the asteroid to alter its orbit. The spacecraft had no scientific instruments or robotic arms, only a digital eye and a suicidal mission. The DART spacecraft weighed about 570 kilograms and was launched with the sole objective of hitting Dimorphos at over 22,000 kilometers per hour. In the final moments, it operated autonomously, using an optical navigation system to keep its target in sight. The impact was broadcast live until the last second, when the image froze just before the collision. Even with its simple structure, the spacecraft managed to accurately hit a target the size of a football stadium, an unprecedented achievement in the history of space engineering. The goal was to determine whether the impact could alter Dimorphos's orbit around Didymos. Before the collision, the orbital period was 11 hours and 55 minutes. After the mission, scientists measured a 32-minute reduction in that time, a result far beyond expectations. For the first time, humanity managed to intentionally change the motion of a celestial body. This practically validated the possibility of planetary defense through kinetic impact. Dimorphos posed no risk to Earth, but its orbit around another asteroid made precise measurements easier. The binary system allowed telescopes on Earth to observe changes in brightness as the celestial bodies eclipsed each other. This made it possible to calculate with extremely high accuracy the effect of the impact, and it eliminated any risk of dangerous deflection. It was a smart choice, ensuring safety and reliable data. The impact generated a cloud of debris that spread through space and could be observed in multiple wavelengths. This provided important clues about the asteroid's internal composition. The surface, which seemed solid, turned out to be much more porous than expected, like a loosely packed pile of rocks. This information will be crucial for modeling the behavior of future targets. After all, the effectiveness of an impact depends directly on the object's structure. DART's success lies not only in the collision, but in the validated concept. The idea of using space as a direct action field for humanity gained concrete proof. For the first time, we didn't just observe a cosmic threat, we interfered with it. And we showed that with planning, we can act preventively. This changes humanity's role in the solar system from spectator to active participant. The mission's cost was relatively low by space standards, around $330 million, a modest sum considering the potential to save the planet from catastrophe. This cost-effectiveness caught the attention of governments and space agencies. If an investment of this size can divert an asteroid, creating an international planetary defense force becomes a matter of political will, no longer just a theoretical idea. The mission also paved the way for future stages. In 2024, ESA, the European Space Agency, will launch the Hera mission, which will visit the impact site and study the effects in detail. This second phase will allow for a better understanding of the resulting crater, mass redistribution, and potential structural changes in Dimorphos. The DART plus Hera combination will create the first controlled rehearsal of asteroid deflection in human history, a kind of orbital laboratory to prevent extinctions. Another highlight of DART was its autonomy. The spacecraft operated alone in the final hours, with no direct human control. This was essential as the response time between commands from Earth and the spacecraft would have been too long. The onboard artificial intelligence was able to track Dimorphos, ignore visual distractions, and focus on Dimorphos. It was a demonstration of how autonomous technologies can be crucial in future precision missions, especially in high-risk environments. Interestingly, the mission had a strong symbolic and cultural impact. Seeing a human-built spacecraft strike a distant asteroid with such precision sparked a mix of fascination and relief. For many, it was the first time the idea of planetary defense stopped being cinematic fiction. Science proved capable of dealing with a real, cosmic problem. The narrative changed. We are vulnerable, yes, but also ingenious. Even among experts, there were doubts whether such a simple impact would produce measurable results. The change in Dimorphos's orbit surprised even the most optimistic engineers. This showed that the direct impact method is not only feasible, but effective, and it reignited interest in other complementary strategies, such as gravitational tugging, controlled explosions, or even using solar sails to slowly alter dangerous orbits. SOHO, Solar and Heliospheric Observatory. The SOHO Observatory was launched in 1995 with an ambitious mission: to continuously monitor the Sun, its activity, and its effects on the space surrounding Earth. Positioned at the Lagrange point L1, about 1.5 million kilometers from the planet, it maintains a constant view of our star. This location allows the satellite to stay in gravitational equilibrium between Earth and the Sun, without needing frequent position corrections. This ensures ideal stability for prolonged observations. Its main function is to study space weather and anticipate dangerous solar events. SOHO has become a fundamental tool for forecasting solar storms, phenomena capable of causing major damage on Earth. When the Sun emits a coronal mass ejection, charged particles travel through space and can strike satellites, navigation systems, and power grids. The observatory can detect these emissions in advance, allowing for rapid alerts. These alerts help operators shut down sensitive equipment or change satellite orbits. On several occasions, this has prevented widespread failures. Beyond its practical function, SOHO has also revolutionized solar physics. It features instruments that analyze oscillations on the Sun's surface, a field known as helioseismology. With this data, scientists have inferred details about the Sun's internal structure, such as rotation patterns and energy transport. This has improved theoretical models of the core's dynamics and the convection zone. The observatory also helped map the star's magnetic activity cycle. One of SOHO's most important instruments is the coronagraph, which blocks direct sunlight to reveal its outer atmosphere. With it, researchers have clearly observed plasma ejections and gained a better understanding of the solar corona. The corona, though much less dense than the solar surface, reaches much higher temperatures. This paradox, still not fully explained, is one of the areas continuously investigated by the satellite. SOHO has been essential in consolidating the importance of such studies. Another remarkable aspect of the mission is its longevity. Originally planned to last 2 years, the operation has extended for decades. A combination of robust hardware, remote software updates, and engineering adjustments enabled its survival. This has made SOHO a continuous source of data on long-term solar variability. With more than 25 years of uninterrupted observations, its archive has surpassed millions of images and measurements. Few scientific instruments have maintained such consistency. Although its focus is the Sun, SOHO also excelled in an unexpected area: the discovery of comets. With its sensitive camera and specific field of view, the observatory became the most prolific comet discoverer in history. To date, it has identified over 4,000 of them, many of the sun grazer type, which pass extremely close to the Sun and disintegrate. These observations have improved our understanding of the dynamics of small bodies in the inner solar system, and they opened new lines of research in cometary astronomy. The mission is operated remotely from Earth, with commands regularly sent to adjust parameters and calibrate instruments. Altogether, the satellite carries 12 main scientific experiments, covering spectra such as ultraviolet, visible light, and radio. This diversity enables simultaneous analysis of different solar layers and processes. The teams involved include scientists from various nationalities and institutions. It is a collaboration between NASA and ESA, with the involvement of universities and research centers. The data generated by SOHO is public and used by space weather monitoring centers worldwide. Institutions like NOAA, ESA, and aerospace defense networks rely on its alerts to coordinate preventative actions. Additionally, amateur astronomers and educators have free access to the satellite's visual records. This has democratized access to solar information and increased interest in heliospheric studies. The mission also laid the groundwork for the development of more recent satellites. Over the years, SOHO has faced serious technical challenges. In 1998, the mission lost contact with Earth during a software update. There were nearly 4 months of silence until engineers managed to re-establish communication. This episode required complex recovery maneuvers and highlighted the team's resilience. The full recovery of the mission was considered a milestone in space engineering history. Since then, safety protocols have been improved to prevent future incidents. The importance of SOHO has grown alongside the advancement of terrestrial technology. The more society depends on satellites, power grids, and automated systems, the greater the impact of solar disturbances. The observatory provides the front line of detection for such risks. It acts as an early warning antenna against potentially disruptive solar explosions. This strategic function has made the satellite a key part of the global invisible infrastructure. Without it, space weather forecasts would be far less accurate. Even with new solar observatories entering operation, such as Solar Orbiter and the Parker Solar Probe, SOHO remains relevant. Its fixed position at L1 offers a unique, constant, and predictable view of the Sun. It serves as a cross-reference for data collected by other missions in different orbits. This complementarity allows solar events to be compared from multiple angles, and it improves real-time modeling of extreme events. The mission's longevity has made it valuable for statistical analysis and long-term forecasts. With solar cycles lasting 11 years, the continued operation of SOHO over several decades allows scientists to study subtle variations from one cycle to another. This is essential for refining climate models based on solar activity. Its data archive has become one of the most comprehensive ever produced about a star, and it continues to expand every day. TESS, Transiting Exoplanet Survey Satellite. The TESS mission was launched by NASA in 2018 with a clear objective: to find exoplanets around nearby stars. Its name stands for Transiting Exoplanet Survey Satellite, and it operates using a simple yet powerful technique. TESS monitors the brightness of thousands of stars simultaneously, looking for small, periodic drops in light. These dips indicate that a planet may have passed in front of the star. It's an indirect but efficient way to detect distant worlds. The satellite observes large sections of the sky for about 27 days each, covering nearly the entire celestial hemisphere. With each new sector observed, TESS collects data from tens of thousands of stars. What sets the mission apart is its focus on relatively nearby and brighter stars. This facilitates follow-up studies with more powerful telescopes like the James Webb. So far, TESS has identified over 6,000 exoplanet candidates. Among the discovered planets, many have intriguing characteristics. Some are Earth-sized and orbit within the so-called habitable zone, the ideal distance for liquid water to exist.
Others orbit red dwarf stars, raising questions about radiation and habitability. And there are extreme cases, like Neptune-sized planets, that complete an orbit in just a few days. Each new find pushes the boundaries of what we understand as a planetary system. TESS doesn't take pictures of the planets. It detects changes in stellar brightness, and from this, scientists calculate the size, orbit, and other characteristics of the possible planet. When an interesting candidate is detected, ground-based telescopes step in to confirm the discovery. This creates a collaborative network of observatories across the globe. The satellite alone doesn't discover worlds, it points out where to look more closely. Unlike its predecessor, the Kepler telescope, which focused on specific and distant regions, TESS scans much larger areas of the sky. It was designed to find exoplanets that are more accessible for detailed study. This strategy aims to make the search for habitable worlds more practical and measurable. The idea is to identify planets that can be investigated more thoroughly in the coming decades. This includes atmospheric analysis and potential chemical signs of life. TESS's sensors were optimized to detect transits of stars with stable brightness and low noise. Even with relatively compact instruments, its sensitivity is remarkable. The 4 sensors cover a wide field of view, equivalent to 85% of the sky. This broad reach allows for large-scale data collection, which accelerates the pace of discoveries. TESS is a planetary screening machine. The mission plays an essential role in this new phase of astrobiology. By identifying candidate planets in habitable zones, TESS lays the groundwork for deeper investigations. Studying atmospheres, chemical composition, and biological signatures first requires knowing where to look. TESS provides this initial map with high efficiency. It's a tracking tool that anticipates the future of exoplanet exploration. Many of the planets discovered orbit stars different from the Sun, including cool dwarfs, binary stars, and even pulsars. This diversity shows that planets are more common than once thought. The mission helps answer fundamental questions. Are systems like ours common? Is Earth an exception, or part of a pattern? TESS provides data so these questions can be addressed statistically, not just theoretically. The mission is also a model of cost efficiency. With a budget of about $200 million, TESS delivers continuous, accessible, and collaborative scientific output. Its operation is simple, and its analysis heavily depends on the global scientific community. Many published papers based on its data are produced by students, universities, and amateur observers. This openness accelerates science and increases the diversity of interpretations. TESS also contributes to the understanding of stellar physics itself. By monitoring the brightness of so many stars over long periods, it provides detailed light curves that reveal variations, pulsations, and flares. This helps scientists understand the life, cycles, and stability of stars. In many cases, the discovery of a planet is merely a byproduct of stellar data. The mission therefore goes beyond what its name suggests. With the arrival of the James Webb Telescope, many exoplanets discovered by TESS have become priority targets. This reinforces the mission's role as an intelligent filter for future investigations. It's as if TESS is compiling a list of interesting worlds for the next decades of exploration. A silent but fundamental job for those seeking to understand life beyond Earth, and one that has already become indispensable in modern astronomy. The mission remains active and is expected to continue operating in the coming years with new extensions planned. Its database keeps growing, and new artificial intelligence tools are being applied to detect subtle patterns. The search for exoplanets is entering a more refined phase. TESS is the radar that shows where to look, and the more it observes, the more it seems full of possibilities. Beresheet, the Beresheet mission, developed by an Israeli company called Space-Il, was a bold attempt to land a spacecraft on the Moon with a minimal budget. Launched in 2019 aboard a SpaceX Falcon 9 rocket, the mission drew attention for being almost entirely private. It was the first time a country without a traditional space agency attempted a lunar landing. The spacecraft weighed only 585 kilograms and had a compact design, adapted for extreme resource efficiency. Its goal was to make history as the first successful commercial lunar mission. The name Beresheet means Genesis in Hebrew, symbolizing a new beginning for Israel in the space race. The project began as part of the Google Lunar X Prize, an international competition offering prizes for privately funded lunar landings. Even after the official end of the prize, the team chose to move forward. The launch took place in February 2019, and the spacecraft spent weeks adjusting its orbit before reaching a lunar trajectory. Its spiral path saved fuel, but required extreme precision. Beresheet successfully entered lunar orbit, a remarkable feat for a low-cost mission. During its final descent, everything appeared to be going well until the last minutes. However, a gyroscope failure interrupted the main telemetry signal. The spacecraft lost orientation control, shut down its engines, and ended up crashing into the moon's surface at over 500 kilometers per hour. Despite the impact, the mission was widely considered a technological and symbolic success. The probe carried simple scientific instruments, including a magnetometer to measure the moon's magnetic field. It also carried a time capsule with cultural symbols of Israel, such as the Hebrew Bible, national anthems, and digital archives of Jewish history. The mission didn't aim to conduct major experiments, but rather to demonstrate technological capability. The mere fact that it came so close to landing with such limited resources was seen as a remarkable achievement. The team behind it, composed of young engineers and volunteers, showed that space missions don't need to cost billions. The total cost was about $100 million, a tiny amount compared to other lunar attempts. This opened the door to a new era of accessible space exploration. Smaller countries and companies began to consider their own lunar projects. Beresheet became a symbol of this paradigm shift. The mission's impact was felt across multiple sectors. In Israel, there was a surge of interest in science and engineering among students. Media coverage was intense, and public engagement far exceeded expectations. SpaceIL immediately announced plans for a second mission, with improvements and new objectives. The failed landing didn't halt the project. On the contrary, it strengthened its relevance. Beresheet 2 is under development and expected to launch again later this decade. Technically, the mission also provided useful data on orbital maneuvers and communication in low-gravity environments. Even without a successful landing, Beresheet proved it's possible to reach the moon precisely using alternative navigation methods. This approach benefits future missions that prioritize lightweight, low cost, and autonomy. The mission became a case study in universities and space agencies, and it inspired new educational projects focused on robotics and exploration. The failure was thoroughly analyzed and attributed to the lack of critical redundancy in the navigation systems. Since the mission operated on a tight budget, many components were simplified. This increased the risk of a single-point failure, as happened with the gyroscope. The lesson learned served to improve contingency protocols in small probes. The next mission aims to address these issues with affordable and effective solutions. The idea is to retain the original spirit, but with greater robustness. Even without a successful landing, Beresheet became the first privately built spacecraft to reach lunar orbit. This changed the logic of space exploration, once dominated by governments and superpowers. The idea of space democratization gained traction after its attempt. Other startups around the world began planning their own missions. The moon stopped being a destination for the few. It became accessible, at least in theory, to anyone with creativity and engineering. The mission also sparked reflections on the role of culture in space exploration. The time capsule carried by Beresheet proposed a symbolic connection between history, identity, and science. This gave the mission an unexpected humanistic dimension. Even though it was technically simple, it carried emotional and collective meaning, a way to show that space can also be a cultural expression, and that humanity's presence beyond Earth isn't limited to science. Space IL remains active, focused on scientific education and promoting innovation. The social impact of Beresheet in Israel was considered more valuable than any data obtained. It demonstrated that technical failure doesn't prevent strategic success, and that space can be a field where new ideas, even incomplete ones, generate waves of transformation. It was an attempt and a foundation for what comes next. The second mission, Beresheet II, aims to launch 2 landers and 1 orbiter, multiplying the objectives of the original mission. The approach will be more conservative in technical terms, but still based on innovation and low cost. The previous failure serves as the foundation for the new project, and it reinforces the role of experimentation as part of progress. The Moon remains the destination, now with more lessons learned. Tianwen-1. In 2021, China accomplished something no other country had done before. It entered Mars orbit, landed on its surface, and deployed a rover, all on its very first attempt. The mission, named Tianwen-1, was launched by the China National Space Administration, or CNSA, and marked a major milestone in space exploration. It consisted of an orbiter, a lander, and the Zhurong rover, all traveling together aboard a single launch vehicle. After a 7-month journey, the spacecraft successfully entered Martian orbit in February. In May, the lander and rover touched down on the Utopia Planitia region. This ambitious all-in-one approach was a high-risk strategy. Most nations had attempted such feats in stages, across multiple missions. Yet Tianwen-1 executed them all in one go, with no prior landing experience on Mars. The success immediately placed China as the 3rd nation to land and operate a spacecraft on the Red Planet, after the US and the Soviet Union. The achievement demonstrated not only technical capability, but also confidence in mission planning. It was a bold entry into deep space exploration. The Zhurong rover, named after a mythical fire god, was designed to study Mars's surface environment. It carried 6 scientific instruments, including a ground-penetrating radar, a magnetic field detector, and weather sensors. These tools allowed scientists to examine the subsurface structure, look for ice, and monitor local climate. Its solar-powered design enabled months of mobility and observation. Unlike previous rovers, it also had a built-in hazard avoidance system. The rover weighed about 240 kilograms and measured 1.8 meters in height. After deploying successfully, it rolled onto the Martian soil and began its autonomous exploration. It captured high-resolution images, conducted soil analysis, and surveyed terrain features. The data collected added to our understanding of Utopia Planitia, a region believed to have once held ancient water. Zhurong's findings are still being analyzed by researchers worldwide. Meanwhile, the orbiter continued circling Mars, serving both as a relay for the rover and as a scientific platform. It carried its own suite of instruments to study the Martian atmosphere, magnetic field, and ionosphere. The dual operation of orbiter and rover created a complete observation system. This allowed synchronized studies from orbit and ground level, something rare in planetary missions. Tianwen-1 provided a 3D picture of Mars with unprecedented coordination. The success of Tianwen-1 wasn't just technical, it was strategic. It showcased China's ability to design, launch, and manage complex interplanetary missions independently. With no reliance on foreign infrastructure, China established itself as a new leader in space science. The mission also marked the beginning of China's long-term Mars exploration program. Future goals include sample return missions and potential crewed exploration. Tianwen-1's development timeline was remarkably fast. The entire mission went from concept to launch in under 6 years. Its success, despite this compressed schedule, speaks to the maturity of China's aerospace industry. The mission also benefited from lessons learned by international missions, but adapted them into a new framework. Instead of following the established step-by-step path, Tianwen-1 redefined what was possible in a single attempt. The Zhurong rover was designed with redundancy in mind, increasing its chances of survival in the harsh Martian environment. Its 6-wheel design allowed it to cross rocks, dunes, and slopes with relative ease. Built-in sensors monitored temperature, tilt, and dust accumulation on its solar panels. The team also implemented an emergency hibernation mode in case of sandstorms or prolonged darkness. These features helped extend the mission's lifespan. The mission emphasized autonomy. Due to the long communication delay between Earth and Mars, real-time control isn't possible. Zhurong software allowed it to make decisions on navigation, obstacle avoidance, and power management. This made the rover more adaptable to changing terrain and environmental conditions. It also reduced the operational burden on mission control, making long-duration operations more feasible. Tianwen-1 generated international interest, even among agencies not typically aligned with China. Scientists from multiple countries requested access to its data. The mission fostered new discussions about collaboration, transparency, and the role of emerging powers in space. While political considerations remain, the scientific impact was undeniable. Tianwen-1 earned a place among the most efficient planetary missions to date. Its success also laid the foundation for Tianwen-2, a planned asteroid sampling mission, and for China's upcoming Mars sample return project. These initiatives aim to go further, bringing Martian soil back to Earth for detailed study. Tianwen-1 was never meant to be a one-time achievement. It was a gateway to long-term exploration and a declaration of technological readiness. The mission closed a gap and opened many doors. Today, both the orbiter and rover have exceeded expectations. Even after Zhurong entered hibernation in 2022, the orbiter remains active and continues its observations. Tianwen-1 is still contributing to global Mars science. Its data is reshaping our understanding of the Martian climate, surface geology, and magnetic environment, and its legacy continues to influence the design of future missions across multiple nations.
InSight. NASA's InSight mission landed on Mars in November 2018 with a unique goal to study the planet's interior. Unlike previous rovers focused on surface exploration, InSight remained stationary. It deployed a seismometer and a heat probe designed to measure geological activity and subsurface properties. This was the first time Mars quakes could be directly recorded. The mission sought to understand the structure and behavior of the Martian crust, mantle, and core. The seismometer, called SACE, was placed directly on the ground by a robotic arm. It was enclosed in a dome to protect it from wind and temperature changes. The instrument was extremely sensitive, capable of detecting vibrations smaller than the width of a hydrogen atom. SACE recorded over 1,000 seismic events during its operational life. These included both shallow quakes and deep, distant tremors. Some quakes were linked to meteor impacts, helping scientists estimate Mars's crust thickness and energy transfer. Others hinted at ongoing internal processes, suggesting the planet remains geologically active. The patterns observed differed from those on Earth due to Mars's smaller size and lack of plate tectonics. InSight provided data to build new seismic models unique to the Martian environment. The findings confirmed that Mars is not a completely dead world. InSight also carried the HP-3 instrument,
a heat probe designed to burrow several meters underground. Its goal was to measure how heat flows from the interior toward the surface. However, the probe encountered unexpected soil resistance and was unable to reach the intended depth. Despite this, partial data were still useful. The experience revealed challenges in predicting Martian soil behavior. It also emphasized the importance of testing for variable terrain. A third major component was the RISE experiment, which measured tiny wobbles in Mars's rotation. This allowed researchers to infer details about the planet's core. Combined with seismic and thermal data, RISE added a new layer to the understanding of Martian dynamics. Together, these instruments formed a trio of deep planetary diagnostics. InSight became the most complete internal survey ever conducted on another planet. The mission was managed from NASA's Jet Propulsion Laboratory and relied on solar power to function. Its large solar panels collected energy for its instruments, communications, and thermal regulation. However, dust accumulation gradually reduced their efficiency. By the end of 2022, power levels dropped too low to sustain operations. InSight eventually went silent, not due to failure, but natural limitations of its environment. Before that, the mission exceeded expectations in both duration and scientific return. Originally planned for 2 years, it operated for over 4. Its data changed how scientists modeled the evolution of rocky planets. Findings from InSight are already being used to interpret similar data on Earth, the Moon, and even exoplanets. The mission bridged planetary science and seismology in ways not previously possible. InSight also served as a platform for testing new engineering techniques. The deployment of instruments using a robotic arm was a first for Mars. Remote installation of sensitive devices, like a seismometer, required unprecedented precision. The mission demonstrated that even stationary landers can yield complex, high-value science. And it helped refine the protocols for future robotic operations on other worlds. Public interest was high during InSight's early days, especially when it captured the sound of Martian wind. These recordings were shared widely and gave people a visceral sense of Mars as a real place. Later, the detection of quakes added emotional weight to the mission. Hearing the heartbeat of another planet was a powerful moment in space exploration. It connected people to Mars not just visually, but physically. The mission's success came despite several challenges. The heat probe issue, dust storms, and power limitations were all significant hurdles. Yet each obstacle became a source of learning for future missions. InSight's team adapted in real time, modifying plans and extending science goals. This flexibility showed how Mars missions must remain dynamic and responsive. It also highlighted the unpredictability of Martian terrain. InSight's seismic archive will remain a crucial resource for years to come. Its recordings offer a baseline for all future geophysical studies of Mars. They also serve as a foundation for developing new methods of detecting subsurface structures. This includes identifying potential lava tubes, aquifers, or ice pockets. InSight didn't just measure quakes, it helped open a window into Mars's hidden layers. As of now, InSight is no longer active, but its impact on planetary science continues. It proved that even a small, immobile lander can change how we understand a planet. The mission redefined expectations for surface stations and set new standards in interplanetary geophysics. Its legacy lies not in movement, but in depth, the kind measured in vibrations, heat, and rotational shifts. InSight truly lived up to its name.
James Webb Space Telescope, JWST. The James Webb Space Telescope, JWST, launched in December 2021 after decades of development, delays, and high expectations. It is the most powerful space telescope ever built.
designed to observe the universe in infrared wavelengths. Unlike the Hubble telescope, which orbits Earth, JWST is positioned at the second Lagrange point, L2, 1.5 million kilometers away. This location provides a stable, cold environment, crucial for detecting faint thermal signals. Its mission is to see deeper into space and further back in time than ever before. JWST's 6.5-meter primary mirror is made of 18 gold-coated hexagonal segments. It unfolds in space after launch, forming a massive light-gathering surface. This allows the telescope to detect extremely faint objects, including galaxies formed just a few hundred million years after the Big Bang. Its sensitivity is so high that it can see the light of stars and galaxies over 13 billion years old. The telescope gives humanity a glimpse of the universe in its infancy. Infrared observation is key to JWST's power. Light from the most distant galaxies is stretched into the infrared by cosmic expansion, a phenomenon known as redshift. Observing in this spectrum allows JWST to see through dust clouds and peer into regions where stars and planets are forming. It can study galaxies, nebulae, exoplanets, and even the atmospheres of alien worlds. This broad scientific range sets JWST apart from any previous observatory. One of JWST's most talked about capabilities is its ability to analyze exoplanet atmospheres. By measuring tiny changes in starlight during a planet's transit, it detects molecular signatures like water vapor, carbon dioxide, and methane. These observations are essential in the search for potentially habitable planets. JWST is already reshaping the conversation around life beyond Earth. It has identified complex atmospheres in planets previously considered unremarkable. The telescope's sunshield is another engineering marvel. About the size of a tennis court, it protects the instruments from solar heat and light. The shield consists of 5 ultra-thin layers of kapton, designed to reduce the temperature by over 300 degrees Celsius. Without it, the sensitive instruments would be blinded by heat. Its successful deployment was one of the most complex operations in space mission history. It unfolded flawlessly during JWST's journey to L2. JWST operates with 4 main scientific instruments, each designed for different types of analysis. These include the near-infrared camera, NIRCam, the mid-infrared instrument, MIRI, the near-infrared spectrograph, NIRSpec, and the fine guidance sensor. Each component adds a unique capability to the telescope's toolkit. Together, they offer an unprecedented view of the cosmos in motion and formation. The combined resolution and sensitivity are unmatched. The telescope is not limited to deep space. It also observes objects within our solar system, including Mars, Jupiter, Saturn, and even distant comets. This versatility broadens its impact, connecting planetary science with cosmology. It can study atmospheres, rings, and moons in high detail. These close-up observations help contextualize what we see in other systems. The telescope bridges the gap between local and distant astronomy. JWST's data is open access, meaning astronomers around the world can apply for time and analyze results. This has led to an explosion of scientific papers and discoveries since its first images were released. Its iconic debut image, a deep field full of galaxies, stunned both scientists and the public. It compressed billions of years of cosmic history into a single snapshot. The level of detail revealed new structures and interactions between galaxies. The mission is expected to last at least 10 years, possibly more depending on fuel and hardware performance. Its location makes it impossible to service, unlike Hubble, which benefited from astronaut repairs. This puts enormous importance on the accuracy of its systems and initial deployment. So far, the telescope has exceeded performance expectations across all metrics. Every image continues to push the limits of what we know. JWST also complements other telescopes like Hubble and Spitzer by extending their observations into new wavelengths. While Hubble sees primarily in visible and ultraviolet, JWST picks up where it leaves off in the infrared. This partnership enhances our multi-wavelength view of the universe. Scientists can now stitch together broader, more complete models of how galaxies evolve. The result is a richer, more detailed cosmic narrative. JWST also is changing science education and public outreach. Its images have become cultural phenomena, bringing astrophysics into mainstream conversation. From classroom walls to social media, JWST is reshaping how people visualize the universe. Its influence extends far beyond the scientific community. The mission reaffirms the role of space science as a source of wonder, inspiration, and collective curiosity. JWST represents a leap in observational astronomy, not just a continuation. It allows us to study how stars form, how galaxies grow, and how planets might support life, all with unprecedented clarity. Its contributions are ongoing and cumulative, fueling discoveries that will redefine astronomy for decades. JWST is a lens into the distant past, but also a tool for future exploration, and it's only just begun.
Parker Solar Probe. The Parker Solar Probe is humanity's first spacecraft to touch the Sun, flying directly through its outer atmosphere. Launched in August 2018 by NASA, the probe is on a long-term mission to study the solar corona, the hot, mysterious region that extends millions of kilometers into space. The corona is where the solar wind originates and where temperatures soar to over 1 million degrees Celsius. Parker's goal is to understand why this layer is so much hotter than the Sun's surface. It is rewriting our understanding of solar physics. To survive its journey, Parker is equipped with an advanced heat shield made of carbon composite. This thermal protection system can withstand temperatures of nearly 1,400 degrees Celsius on the sun-facing side, while keeping the instruments behind it at room temperature. The shield is only 11.5 centimeters thick, but reflects over 99% of solar energy. It allows the probe to fly as close as 6 million kilometers from the solar surface. No other spacecraft has come this close before. The probe carries 4 main instrument suites to measure particles, magnetic fields, electric fields, and imaging data. These instruments operate during each solar flyby, collecting high-resolution data from within the corona. The mission is divided into 24 planned orbits, each bringing the probe closer to the Sun. It uses gravity assists from Venus to shrink its orbit and dive deeper. Each pass provides new insights into the Sun's complex behavior. One of Parker's major objectives is to solve the coronal heating problem. The Sun's surface is about 5,500 degrees Celsius, but the corona is hundreds of times hotter, an apparent contradiction. Theories suggest that magnetic waves or nanoflares may transfer energy outward. Parker's instruments are designed to test these ideas by directly sampling the plasma and fields involved. Early data already point to dynamic interactions never observed before. Another focus is the origin and acceleration of the solar wind, a stream of charged particles constantly flowing from the Sun. This wind shapes space weather and affects satellites, power grids, and communication systems on Earth. Parker is helping scientists understand how and where the wind is formed. These insights could lead to better space weather forecasting. It's not just science, it's a practical concern for modern technology. The spacecraft also records solar storms and magnetic switchbacks, sudden unexpected reversals in the Sun's magnetic field. These features were detected up close for the first time thanks to Parker's proximity. The data suggest that the corona is far more turbulent than models had predicted. This turbulence may play a key role in heating and particle acceleration. Each orbit reveals a new layer of complexity.
Parker Solar Probe's velocity is also a record breaker. It is the fastest human-made object in history, reaching speeds over 690,000 kilometers per hour. This incredible speed allows it to outrun solar material and reposition itself for new observations. Its trajectory is designed with pinpoint accuracy to maintain proximity without sacrificing stability. The balance between speed, distance, and control is an engineering triumph. Communications with Parker are carefully timed. Due to the intense solar radiation, the probe must often operate autonomously. Data is stored on board and transmitted back to Earth during specific windows. Despite these constraints, the flow of information has been continuous and rich. Scientists receive terabytes of data after each pass. The mission continues to produce insights at an impressive rate. The mission is expected to continue into the late 2020s, with each orbit yielding closer approaches. By the final flybys, Parker will travel within 6.1 million kilometers from the Sun's surface. At that point, it will be well inside the corona. No mission has ever operated in such extreme conditions. The longevity and performance of the probe will define the boundaries of what space engineering can achieve. Parker Solar Probe is also a tribute to solar physicist Eugene Parker, who first theorized the solar wind in the 1950s. It is the first NASA mission named after a living scientist. Parker witnessed the launch of the probe named in his honor. This human connection adds depth to the mission's scientific legacy. It links decades of theory with real-time exploration. The mission complements other solar observatories, like SOHO and Solar Orbiter. While those observe the Sun from afar, Parker offers direct sampling. The combined data sets allow researchers to model the Sun's behavior across multiple scales. This collaboration improves forecasts of space weather events, and it deepens our understanding of how solar activity shapes our solar system. The Parker Solar Probe is not just a technological marvel. It is a mission that places our instruments inside the furnace of the star. It provides answers to long-standing questions about solar activity, magnetic fields, and plasma dynamics. Each close pass brings us closer to understanding the forces that govern our cosmic neighborhood, and the Sun, once too dangerous to approach, is finally within reach.
New Horizons, launched in January 2006 with a clear target: Pluto, the last unexplored classical planet in the solar system. At the time, Pluto had never been visited, and its distant location made it one of the most mysterious bodies in our neighborhood. The spacecraft took 9.5 years to reach its destination, traveling at over 50,000 kilometers per hour. It performed a gravity assist at Jupiter to increase its speed. In July 2015, it became the first human-made object to fly past Pluto. The flyby lasted only hours, but the data revolutionized planetary science. What was once a blurry dot became a complex world with mountains, plains, and possible subsurface oceans. One of the most striking features was a heart-shaped region called Sputnik Planitia, a vast ice plain of nitrogen and methane. Surface temperatures measured around -230 degrees Celsius. Pluto's thin atmosphere, composed mostly of nitrogen, was seen escaping into space like a comet's tail. New Horizons carried a suite of instruments designed to map Pluto's surface, analyze its composition, and measure its atmosphere. These included a high-resolution camera, spectrometers, and a dust counter. The mission was designed for speed, not orbit, so it couldn't slow down or circle the planet. Instead, it captured thousands of images and readings during debrief encounter. Data transmission continued for over a year after the flyby, due to limited bandwidth and distance. The mission didn't end at Pluto. After the successful flyby, NASA redirected the spacecraft toward a Kuiper Belt object called Arrokoth.
This object, originally nicknamed Ultima Thule, is one of the most primitive bodies ever studied. New Horizons flew past it on January 1, 2019, the farthest close encounter ever conducted by a spacecraft. Artemis is a contact binary, two lobes fused together, shaped like a snowman. Its structure preserves the conditions of the early solar system. Studying Artemis provided rare insight into how planetesimals, the building blocks of planets, formed. Its smooth surface and undisturbed layers suggested a slow, gentle formation process. This challenged older models of violent collisions and instead supported accretion by low-velocity aggregation. The flyby added a new piece to the puzzle of planetary origins. New Horizons effectively extended the frontier of human exploration into deep time and deep space. The spacecraft itself is about the size of a baby grand piano and powered by a nuclear RTG, radioisotope thermoelectric generator. Solar panels were not feasible at such distances where sunlight is weak. The RTG provided reliable energy for the spacecraft's instruments, heaters, and communication systems. Its design needed to withstand extreme cold, radiation, and long durations without repair. New Horizons remains operational and continues to send data from the Kuiper Belt. Its current trajectory carries it further into the outer solar system, where it observes cosmic background radiation, charged particles, and distant dust. Though past its primary targets, it continues to function as a probe of the interplanetary environment. Few missions operate at such vast distances. It has traveled over 8 billion kilometers from Earth and remains one of our most distant scientific instruments. Communication with New Horizons takes several hours due to its immense distance. Commands must be planned in advance, and responses are delayed. This requires a high level of autonomy on board, with preloaded instructions and automatic error handling. The mission team monitors its health using brief telemetry windows. Despite these limitations, the spacecraft continues to perform well. New Horizons also demonstrated the value of long-term mission planning. Launched when Pluto was still a planet, it arrived after its reclassification as a dwarf planet. Yet its findings reignited debates about Pluto's planetary status. The detailed imagery and scientific data far exceeded expectations. The mission proved that even minor bodies can hold major surprises. It shifted focus from classification to exploration. Public interest in New Horizons surged during the 2015 flyby. Live updates, visualizations, and data releases captured global attention. The heart-shaped feature on Pluto became a symbol of scientific achievement and curiosity. The mission helped inspire a new generation of planetary scientists. It showed that even after decades of exploration, the solar system still holds mysteries. New Horizons has no brakes and no return path. It will drift through the Kuiper Belt and eventually into interstellar space. Its signal will one day fade, but its contribution to science will remain. The mission has fundamentally changed how we understand planetary formation, distant objects, and the edges of our solar system. New Horizons opened a window to a region we had only imagined.
Chang'e 4. Chang'e 4, launched by China in December 2018, was the first mission in human history to land on the far side of the Moon. Unlike the near side, always facing Earth, the far side is never visible due to tidal locking. This region had never been explored from the surface because direct communication is impossible. To solve this, China launched a relay satellite named Qichao, positioned at the Earth-Moon L2 point. This enabled Chang'e 4 to send and receive data from the hidden hemisphere. The mission consisted of a lander and a rover named U-22, or Jade Rabbit 2. It landed successfully in January 2019 inside the Von Karman crater within the South Pole Aitken Basin. This is one of the oldest and deepest impact basins in the solar system.
The choice of landing site was deliberate. Scientists hoped to study lunar material from deep within the crust. The region also provided unique terrain and radiation conditions. Yutu-2 became the first rover to operate on the far side of the Moon. Its instruments include a panoramic camera, ground-penetrating radar, spectrometers, and an infrared imaging system. These tools allow it to study soil structure, composition, and thermal properties. The rover has traveled over 1,000 meters across the crater floor. It continues to operate far beyond its original mission timeline. One of the mission's most intriguing findings was the detection of materials potentially originating from the lunar mantle. These may have been exposed by past impacts and studied directly by the rover's instruments. Yutu-2's radar also revealed multiple underground layers beneath the surface. These findings suggest a complex geological history in this region of the Moon. The data is still being analyzed by scientists around the world. Chang'e 4 also included a small biological experiment, a sealed container with seeds and insect eggs. It was the first attempt to test biological growth on the Moon's surface. While most of the organisms did not survive the extreme temperature fluctuations, the cotton seeds briefly sprouted. This marked the first time a plant germinated on another world. Though symbolic, the experiment raised important questions about sustaining life beyond Earth. The mission demonstrated advanced autonomous landing and obstacle avoidance. Because it landed in an uncharted region with no GPS, Chang'e 4 relied on terrain recognition and preloaded maps. Its landing was precise and smooth, despite the rugged terrain. This showed China's growing capability in lunar navigation and surface operations. It also served as a test bed for future, more complex landings. The Kuei-Chao relay satellite was critical to the mission's success. Positioned behind the Moon from Earth, it enabled constant communication between the lander and mission control. This was the first time such a relay system had been used for a lunar mission. The concept proved so effective that it is being considered for future deep space missions. It laid the groundwork for permanent exploration on the lunar far side. The mission's long-term goal is part of China's broader lunar strategy. It fits into a roadmap that includes future sample return missions, a possible moon base, and cooperation with other nations. Chang'e 4 represented not only a technological success, but also a geopolitical signal. It demonstrated China's ability to innovate independently and execute complex space missions. The far-side landing was a clear declaration of capability. Despite being far from Earth, the mission received global scientific attention. Its findings were published in leading journals, and data was shared with the international community. The mission broke the perception that the Moon was already fully explored. Instead, it revealed how much we still have to learn, especially in regions previously unreachable. Chang'e 4 renewed interest in lunar science. The rover's solar-powered design allows it to sleep during the long, cold lunar nights. Each lunar day lasts about 14 Earth days, followed by 14 days of darkness. Despite harsh conditions, Yutu-2 has survived over 50 lunar nights. This resilience extends the value of the mission and allows for long-term data collection. It has become the longest operating lunar rover in history. Chang'e 4 was not just a technological feat, it expanded our scientific frontier. By accessing a new region of the Moon, it opened questions about the Moon's asymmetry, crust thickness, and internal composition. It also provided lessons for operating in remote and hostile environments. These insights are essential for future missions aiming at lunar resource utilization or human presence. The mission continues to operate, with the rover sending periodic updates and images. Its legacy lies in proving that exploration of the Moon is far from over. The far side, once a mystery, is now a region of active study. Chang'e 4 redefined what is possible in lunar exploration and set the stage for more ambitious missions to come. Hayabusa. Hayabusa, meaning falcon in Japanese, was a groundbreaking asteroid sample return mission developed by JAXA. Launched in 2003, It aimed to visit the near-Earth asteroid Itokawa, collect surface material, and return it to Earth. At the time, no country had ever brought back samples from an asteroid. The mission faced multiple technical setbacks, but ultimately succeeded. Its return in 2010 marked a historic achievement in precision spaceflight. Itokawa is a small peanut-shaped asteroid about 540 meters long. It lacks gravity strong enough to hold a spacecraft on its surface, complicating landing maneuvers. Hayabusa used a unique approach. It hovered above the asteroid and briefly touched down to collect particles. Instead of digging or drilling, it fired a small projectile to kick up surface dust. The collector then sealed the sample in a return capsule. The spacecraft faced many challenges en route. It lost contact with Earth several times and suffered failures in its attitude control system. 2 of its 4 ion engines failed, and its onboard chemical propulsion system malfunctioned. At one point, only 1 reaction wheel was still operational. Engineers had to improvise novel control methods, including using solar pressure to stabilize the craft. Despite these issues, Hayabusa reached Itokawa in 2005 and mapped its surface in detail. It revealed a rubble pile structure, a loose collection of rocks and dust, rather than solid rock. This changed the understanding of small asteroids, suggesting they form from shattered remnants of larger bodies. Itokawa's surface also showed evidence of thermal fragmentation. These findings expanded models of asteroid evolution. Hayabusa attempted 2 sample collections in late 2005. The first appeared to fail due to a misfire in the projectile mechanism. The second attempt was also uncertain. For years, scientists weren't sure if any material had been captured. But the team pressed on, aiming to return the capsule to Earth regardless. It was a gamble based on engineering instinct, not confirmed data. In June 2010, Hayabusa's sample return capsule re-entered Earth's atmosphere at over 12 kilometers per second. It landed safely in the Australian outback, glowing like a meteor during descent. When the container was opened, researchers found more than 1,500 tiny grains from Itokawa. Most were smaller than a human hair. The successful return made Hayabusa the first mission to bring asteroid material back to Earth. The analysis of the samples revealed valuable insights. They were mostly silicate minerals, similar to those found in meteorites. This confirmed that many meteorites reaching Earth originate from asteroids like Itokawa. The grains also showed exposure to space weathering and micrometeorite impacts. This allowed scientists to estimate how long the asteroid had been exposed to cosmic radiation. Hayabusa's success reshaped expectations for what small space agencies could achieve. JAXA, with fewer resources than NASA or ESA, completed a mission of global significance. The mission also inspired follow-up projects, including Hayabusa 2, which launched in 2014 to the asteroid Ryugu. This time, the spacecraft collected much larger samples and returned in 2020. Hayabusa laid the foundation for this second, more robust effort. The mission emphasized the importance of sample return science. While remote sensing offers valuable information, physical samples enable lab analysis with far greater precision. Techniques like isotope dating, microstructural imaging, and chemical mapping are only possible on Earth. Hayabusa proved that collecting space material is feasible even under extreme constraints. It was a triumph of resilience and adaptation. Public reaction to Hayabusa was strong, especially in Japan. The mission captured imaginations with its underdog story, a damaged spacecraft limping home across space. Documentaries, books, and animations were produced to commemorate its journey. It became a national symbol of perseverance through adversity. The mission's legacy extended far beyond the scientific community. Technically, Hayabusa pioneered low-thrust ion propulsion in interplanetary missions. Its ion engines operated for over 30,000 hours, a record at the time. The mission also demonstrated long-duration autonomous navigation. These technologies have since been adopted in other deep space missions. Hayabusa was not only a science mission, but a platform for engineering innovation. Hayabusa's small container of dust changed how humanity interacts with the solar system. It showed that even tiny remote objects can be reached, studied, and sampled, and that precision, not size, defines the success of a mission. From a distant asteroid to a clean lab on Earth, Hayabusa proved that the gap between worlds is bridgeable, one grain at a time.
Juno. NASA's Juno spacecraft was launched in 2011 to study Jupiter, the largest planet in the solar system. It arrived in orbit in July 2016 and began a series of polar flybys, passing closer to the planet than any spacecraft before. Unlike previous missions, which stayed in equatorial orbits, Juno's trajectory covers north to south. This allows it to observe Jupiter's entire surface and magnetic environment. Its primary goal is to understand the planet's interior and formation. Juno is powered by solar panels, a rarity for missions so far from the Sun. The panels span over 20 meters and generate just enough energy to power its instruments. The spacecraft orbits Jupiter in a highly elliptical path, avoiding prolonged exposure to its intense radiation belts. Each orbit takes about 53 days, with closest approaches, or perijoves, occurring at altitudes of only a few thousand kilometers. These flybys offer unparalleled views of the planet's atmosphere and poles. The mission has revealed Jupiter as a planet of deep complexity. Its iconic bands and storms extend much farther below the cloud tops than previously thought. The Great Red Spot, a massive storm larger than Earth, reaches deeper into the atmosphere than models had predicted. Juno's microwave radiometer measures thermal emissions, revealing layers of structure and movement. These data have changed how scientists view gas giants. Juno also carries a magnetometer to map Jupiter's magnetic field in detail. The field is much stronger and more irregular than expected. In some regions, it is 10 times more powerful than Earth's. These findings suggest that the planet's metallic hydrogen core may be partially diluted, with magnetic elements dispersed unevenly. The data are helping to refine models of planetary magnetism. Understanding Jupiter's field also sheds light on magnetic processes in other planets. The spacecraft observed auroras at Jupiter's poles unlike anything on Earth. These auroras are driven by interactions between the planet's magnetic field and charged particles from its moons and the solar wind. Juno's ultraviolet and infrared instruments captured high-resolution images of these luminous displays. They revealed auroral ovals, flares, and pulsating patterns that vary with magnetic activity. Jupiter's polar regions are dynamic and highly energetic. JunoCam, a visible light camera, was included primarily for public engagement. It has become one of the mission's most beloved features. The images of swirling clouds, polar cyclones, and colorful storms captivated audiences worldwide. Citizen scientists helped process the raw data, creating detailed visuals for public and educational use. This collaboration has made Juno one of the most open and participatory space missions ever launched. The spacecraft's data on gravity have also been groundbreaking. By measuring slight variations in Jupiter's gravitational pull, Juno inferred the planet's internal structure. The findings suggest that Jupiter has a fuzzy core, not a solid mass, but a diffuse region of heavy elements. This challenges traditional models of gas giant formation. It implies a more chaotic early history involving collisions and mixing. Juno has observed strange phenomena, such as polygonal cyclone patterns at the poles. These are clusters of massive storms arranged in geometric shapes. The North Pole has 8 storms in an octagonal pattern. The South Pole has 5 in a pentagon.
These formations remain stable despite their turbulent environment. Understanding their dynamics could reveal new principles of fluid motion in planetary atmospheres. Each orbit gives Juno only a short window for data collection, a few hours near closest approach. Afterward, it transmits the data back to Earth over several days. This operational rhythm repeats with each flyby. The mission team must plan each orbit carefully, balancing scientific objectives and spacecraft health. Juno's systems have proven resilient despite repeated passes through high radiation zones. The mission has been extended multiple times, with new science goals added. These include flybys of Jupiter's moons Ganymede, Europa, and Io. The spacecraft is now offering new views of these icy and volcanic worlds. While not originally designed for moon encounters, Juno's instruments provide valuable observations. It fills the gap until future dedicated missions like Europa Clipper arrive. Juno's design emphasizes autonomy and durability. It carries radiation-hardened electronics housed in a titanium vault. Its navigation relies on a star tracker and inertial sensors, allowing precise maneuvers. The spacecraft has operated flawlessly for years, adapting to changing conditions. Its extended mission proves that robust design pays off in the harsh environment of Jupiter. Juno is still active and transmitting, providing new discoveries with each orbit. It has deepened our knowledge of planetary interiors, magnetospheres, and atmospheric dynamics. Its data will shape theories of gas giant formation for decades. Juno reminds us that even planets we've observed for centuries still hold countless secrets, waiting to be uncovered, one pass at a time. Venera 13. In March 1982, the Soviet Union's Venera 13 became the first spacecraft to transmit color images from the surface of Venus. The planet's surface conditions are among the most hostile in the solar system, with temperatures near 465 degrees Celsius and pressures 92 times that of Earth. Previous landers had survived only minutes under such stress. Venera 13 was built to endure longer, and it did. The lander lasted 127 minutes, far exceeding expectations. Venus has a thick carbon dioxide atmosphere with clouds of sulfuric acid, making descent extremely difficult. Venera 13 used a multi-stage heat shield and pressure-resistant capsule to survive entry. The descent module was equipped with scientific instruments and imaging systems. As it descended, it transmitted atmospheric data on temperature, pressure, and composition. It deployed parachutes to slow its fall, then jettisoned them near the surface. Once on the ground, Venera 13 began transmitting panoramic images using mechanical scanning cameras. These images showed a rocky terrain with flat, fractured slabs, unlike anything seen before. The color photos revealed an orange-brown hue caused by the dense atmosphere's light filtering. The lander also analyzed the surface using a drill that collected a sample for X-ray fluorescence analysis. It found basalt-like rocks similar to some on Earth. One of the mission's engineering triumphs was its ability to function at such high temperatures. The electronics were housed in a pressurized vessel with insulation and active cooling. The interior temperature still rose rapidly, limiting the mission duration. But even with limited time, Venera 13 returned an extraordinary amount of data. Its success demonstrated the value of robust design under extreme conditions. The spacecraft was part of a larger series of Soviet missions to Venus. The Venera program had been operating since the 1960s, with many failed attempts and gradual improvements. Venera 13 built on lessons from earlier landers like Venera 9 and 12. Its twin, Venera 14, launched just days later and achieved similar results. Together, they remain humanity's most successful missions to Venus's surface. Venera 13 also measured the planet's lightning activity, using acoustic sensors to detect thunder-like sounds. This added to the growing evidence that Venus has active weather despite its slow rotation. The data helped refine models of Venusian atmospheric circulation. It also detected high concentrations of sulfur compounds. These findings hinted at complex chemical interactions in the lower atmosphere. The lander carried a microphone, one of the first on another planet. It captured the sound of the wind and internal mechanisms, though the recording was brief. While the audio quality was limited, it marked a milestone in planetary exploration. No other microphone has yet survived on Venus. The data collected by Venera 13 continues to be analyzed decades later. Despite its importance, the mission remains relatively unknown outside Russia. Its images and data were released during the Cold War and did not receive wide coverage in the West. This has led to a historical gap in public awareness. Yet Venera 13's achievements are unmatched when it comes to exploring Venus's surface. It remains the gold standard for high-pressure planetary landers. The success of Venera 13 underscored how little we understand Venus. Unlike Mars, which has seen dozens of missions, Venus has remained largely unvisited. The planet's extreme environment makes it technologically challenging and scientifically tantalizing. Venera 13 proved that exploration is possible even under crushing pressure and intense heat. It set a high bar that has not yet been surpassed. Plans for new Venus missions have emerged in recent years, including NASA's Veritas and ESA's Envision. These future missions will orbit rather than land, focusing on surface mapping and atmospheric studies. Still, no current technology matches Venera 13's ability to survive on the surface. The mission remains a key reference point. Any future lander must match or exceed its resilience. Venera 13 also holds symbolic value. It showed that even the most inhospitable worlds can be reached. The harsh beauty captured in its images brought a distant planet into human view. It helped shift planetary science from distant observation to direct contact. The data it collected gave Venus a surface and a story, one shaped by heat, pressure, and time. The legacy of Venera 13 is not just technical, it's philosophical. It pushed the boundaries of what machines can do and where we dare to go. It turned Venus from a blank spot on the map into a real, tangible place, a world that, for just 2 hours, let a mechanical visitor look, listen, and touch its ancient rocks. Gaia is a European Space Agency mission designed to create the most accurate 3D map of our galaxy ever attempted. Launched in 2013, it orbits around the L2 Lagrange point, about 1.5 million kilometers from Earth. From this vantage point, it avoids Earth's shadow and enjoys a stable environment. The spacecraft carries a billion-pixel camera capable of measuring star positions with micro-arcsecond precision. Its goal? Map over 1 billion stars. Gaia's mission is astrometry, the science of measuring the positions and motions of celestial bodies. It tracks stars over time to determine their distances, velocities, and changes in brightness. The data helps reconstruct the Milky Way's structure and history. It also aids in understanding stellar evolution and the distribution of dark matter. Gaia's measurements are so precise it can detect a hair's width at 2,000 kilometers away. The spacecraft spins slowly as it orbits, scanning the sky in great circles. Each star is observed dozens of times during the mission. These repeated observations allow scientists to detect movement and variability. Over time, Gaia builds a dynamic map of the galaxy. It captures not just where stars are, but how they move and change. This transforms our understanding of galactic dynamics. Gaia's camera system is complex, with 106 CCD detectors and a focal plane over 1 meter wide. The data it collects must be processed by supercomputers on Earth. Each star's motion is calculated using complex algorithms that account for parallax, proper motion, and instrument calibration. The data pipeline involves scientists from around the world. It is one of the most collaborative missions in astronomy. In addition to stars, Gaia detects asteroids, quasars, and distant galaxies. It has discovered thousands of new celestial objects, including ultra-faint dwarf galaxies. These provide clues to how the Milky Way formed and evolved. Gaia also helps predict stellar collisions and close encounters with other stars. Its scope goes beyond static mapping. It reveals cosmic motion on a grand scale. The mission has released several massive datasets known as Gaia data releases. Each release adds new layers of information: colors, temperatures, compositions, orbits, and more. The most recent catalog includes over 1.8 billion stars. It is the largest and most precise star catalog in human history. Researchers use it to test theories from cosmology to exoplanet detection. Gaia has contributed to the search for exoplanets by detecting subtle stellar wobbles. These indicate gravitational influences from unseen planets. It also identifies binaries and star clusters with unprecedented detail. Its findings impact many areas of astrophysics. From black hole candidates to stellar ages, Gaia's reach is immense. It has become a backbone of modern space science. Though Gaia doesn't carry traditional cameras for public images, its data is visualized into stunning star maps. These maps show the Milky Way in motion, revealing spirals, waves, and warps. Animations based on Gaia data have captivated audiences worldwide. The visuals combine art and science, helping people grasp the scale and complexity of our galaxy. The spacecraft is designed for long-term operation, with mission extensions already granted. Its stable orbit and efficient design allow continuous observation. Gaia uses sunlight to power its systems and maintain thermal balance. It transmits data back to Earth daily via the Deep Space Network. So far, it has exceeded performance expectations. Gaia's precision surpasses anything previously possible. Before its launch, most star distances were known only approximately. Now, for billions of stars, we know exact positions and motions. This revolutionizes how we measure cosmic scales. It also calibrates other telescopes and missions. Gaia serves as a universal yardstick for the cosmos. The data has led to surprising discoveries, like star streams from ancient galactic collisions. These trails show how the Milky Way grew by devouring smaller galaxies. Gaia also revealed asymmetries and ripples in the galactic disk. These patterns may have been caused by past impacts or gravitational waves. Such findings reshape our understanding of the galaxy's past. Gaia continues to operate, refining its map of the sky with each passing year. The mission may not offer dramatic images or land on distant worlds, but it quietly transforms astronomy. Its contribution is scale, structure, and precision. Thanks to Gaia, our galaxy is no longer a blur of lights. It is a charted system in motion, with every star in its place, trajectory, and story.
Chandrayaan-1. In 2008, India launched its first lunar mission, Chandrayaan-1. Developed by the Indian Space Research Organization, ISRO, it was a bold step into deep space exploration. The spacecraft entered lunar orbit successfully and remained operational for nearly a year. Its primary goal was to map the Moon's surface using a suite of scientific instruments. But its biggest discovery came from something no one had expected. On board Chandrayaan-1 was a NASA instrument called the Moon Mineralogy Mapper, M3. This device analyzed reflected sunlight to detect chemical signatures on the surface. While surveying the polar regions, M3 found traces of water molecules in the lunar soil. The discovery shocked the scientific community. For decades, the Moon had been considered bone dry. The detection of water molecules was not in the form of lakes or ice sheets, but rather hydroxyl, chemical bonds containing hydrogen and oxygen. These were embedded in surface minerals, especially near the Moon's poles. This hinted that the Moon had undergone more complex chemical processes than previously thought. It also raised questions about the Moon's potential for future human habitation.
The mission carried 11 instruments, including radar, X-ray, and infrared spectrometers. It mapped surface composition, elevation, and mineral distribution with unprecedented detail. Chandrayaan-1 also detected magnesium, aluminum, and uranium on the surface. These findings improved understanding of lunar geology and crust formation. For a first mission, the amount of data returned was extraordinary. A key moment of the mission was the release of the Moon Impact Probe, MIP. This small payload was dropped from orbit and impacted the lunar surface near the South Pole. During its descent, it transmitted data on atmospheric particles and surface characteristics. MIP's measurements helped confirm the presence of water molecules. It was also the first Indian object to reach the Moon. Chandrayaan-1 orbited the Moon in a polar trajectory, allowing global mapping coverage. It maintained an altitude of about 100 kilometers above the surface. Its onboard star sensors and gyroscopes enabled precise navigation. Ground communication was handled from the Indian Deep Space Network. Despite minor technical issues, the mission functioned effectively for most of its planned duration. In August 2009, contact with the spacecraft was unexpectedly lost. ISRO later declared the mission complete, as 95% of its objectives had already been met. The early loss of communication was likely due to thermal issues. Still, Chandrayaan-1 was hailed as a major success. It placed India among the elite group of nations with operational lunar missions. One of the mission's legacies was international collaboration. Chandrayaan-1 included contributions from NASA, ESA, and Bulgarian space agencies. It demonstrated India's ability to work at the frontiers of space science. The data from the mission is still used in global lunar research. It established ISRO as a serious player in planetary exploration. The discovery of lunar water reshaped priorities for future moon missions. Agencies like NASA and ESA began planning missions to explore the polar regions more closely. Water means fuel, life support, and even construction material for lunar bases. Chandrayaan-1 had effectively redefined the Moon as a resource-rich world, not just a dusty rock. ISRO followed up with Chandrayaan-2, which included a lander and rover but experienced a landing failure. Still, the orbiter continues to send back data. Chandrayaan-3 successfully landed in 2023, making India the first country to reach the Moon's south pole. These missions are all built on the foundation laid by Chandrayaan-1. The program is now central to India's space ambitions. Public interest in the mission was high, especially in India. Chandrayaan-1 became a source of national pride and sparked increased investment in space technology. It inspired a new generation of engineers and scientists. The mission was widely covered in Indian media and celebrated in education campaigns. Its impact extended beyond science to culture and identity. Chandrayaan-1 showed that major discoveries can come from modest missions. With a relatively low budget and compact design, it achieved something no other nation had done. It rewrote the Moon's chemical story and influenced exploration strategies worldwide. Proof that transformative science doesn't always require massive rockets, just clear goals, clever instruments, and precise execution.
Artemis I was NASA's first major step toward returning humans to the Moon after half a century. Launched in November 2022, the mission was uncrewed but carried a full-scale version of the Orion spacecraft. Its goal was to test the Space Launch System SLS, the most powerful rocket NASA has ever built. Artemis I marked the beginning of a new era in lunar exploration. It was designed to go farther than any spacecraft built for humans had gone before.
The Orion capsule completed a 25-day journey around the Moon. It entered a distant retrograde orbit, swinging more than 64,000 kilometers beyond the Moon's far side. This orbit had never been attempted with a crewed spacecraft design. The mission tested critical systems like heat shielding, propulsion, life support, and communication. All of them performed better than expected. The SLS rocket produced over 4 million kilograms of thrust at launch. Its twin solid rocket boosters and core stage lifted Orion into space with immense power. After reaching orbit, the upper stage fired to send the spacecraft on a lunar trajectory. The launch was visible across much of Florida and the Atlantic. It was the most powerful liftoff since the Saturn V in the 1960s. Artemis I carried numerous payloads, including CubeSats that explored asteroids, space weather, and radiation. One satellite, BioSentinel, tested how living cells respond to deep space conditions. The mission also included sensors and mannequins inside Orion to simulate crew exposure. These experiments gathered data critical for future astronaut safety. It was a comprehensive test of deep space operations. During its lunar flyby, Orion passed just 130 kilometers above the surface. It captured high-resolution images of the Moon, including the dark side. The spacecraft also relayed live video from space, showing Earth and Moon together. These visuals were widely shared and helped reignite public interest. For many, it was the first real-time glimpse of lunar travel in their lifetime. The mission's return phase was a crucial test of Orion's heat shield. Re-entering Earth's atmosphere at over 39,000 kilometers per hour, the spacecraft endured temperatures near 2,800 degrees Celsius. The shield performed as designed, slowing Orion for a parachute-assisted splashdown in the Pacific Ocean. Recovery teams retrieved it successfully. This validated its safety for future crewed missions. Artemis I was not just a technical demonstration, it was symbolic. It marked NASA's renewed commitment to deep space, moving beyond low Earth orbit. The mission's success paved the way for Artemis II, which will carry astronauts around the Moon. It also supported long-term goals like establishing a lunar base and preparing for Mars missions. Artemis I proved the system is ready. International partners played key roles. The Orion service module was built by the European Space Agency, ESA. Ground support and tracking involved agencies from multiple countries. The Artemis program itself is part of a larger framework called the Artemis Accords. These agreements set principles for peaceful space exploration and resource use. Artemis is not just an American mission, it's global. NASA emphasized sustainability in Artemis's design. Both SLS and Orion were built to be reusable over multiple missions. Future iterations will improve efficiency and cost-effectiveness. Artemis I was the first full test of this approach. Lessons learned will be applied to future flights. The goal is not just to return to the Moon, but to stay. Artemis I also sparked public enthusiasm in a way not seen in decades. Millions watched the launch online and on television. Schools, museums, and science centers held events to follow the mission. The media coverage helped rebuild interest in space travel. Artemis I became a gateway to inspire the next generation of explorers. The mission succeeded on all technical fronts, with only minor issues reported. It demonstrated stable flight, deep space navigation, and successful re-entry. Engineers are now analyzing the data to refine hardware and software. The next steps are already underway. Artemis II and Artemis III are scheduled for later this decade, bringing astronauts closer to lunar soil. Artemis I bridged past and future, combining Apollo's legacy with modern technology. It carried symbolic cargo, like pieces of Apollo 11 and tributes to past astronauts. But it also pointed forward to permanent lunar infrastructure, resource utilization, and human exploration of Mars. It was the first giant leap of this new era, laying the foundation for what comes next. Stardust. Launched in 1999, NASA's Stardust mission was the first to bring back material from a comet's tail. Its target was Comet Wild 2, a small but active body orbiting the Sun. Stardust traveled over 4.5 billion kilometers across deep space. Its goal was to collect dust particles as it passed near the comet in 2004. These particles could offer a glimpse into the solar system's earliest ingredients. To collect them, Stardust used a special material called aerogel, an ultralight silica-based substance. The aerogel tray acted like a sponge, gently capturing particles without destroying them. As the spacecraft flew through the comet's coma at 6.1 kilometers per second, dust grains embedded themselves in the gel. The aerogel array then folded into a return capsule. Stardust also carried instruments to image the comet and measure surrounding gases. The encounter with Wild 2 revealed jets of gas and complex surface features. Stardust took detailed photos showing craters, cliffs, and spires on the comet's nucleus. These structures suggested an active surface shaped by volatile materials. Some jets seemed to erupt from inside the comet, driven by heat. It was a close look at a primitive world rarely observed so directly. After completing its mission, Stardust began its return trip to Earth. In January 2006, it released its sample capsule toward our planet. The capsule entered Earth's atmosphere at over 46,000 kilometers per hour, the fastest re-entry ever for a spacecraft. It landed safely in the Utah desert using a parachute system. Recovery teams quickly secured it for laboratory analysis. Scientists examined the captured particles under microscopes and advanced scanning tools. They discovered microscopic grains made of silicates, sulfides, and organic compounds. Some materials resembled those found in interstellar dust. Others suggested high-temperature origins near the young Sun. The samples gave clues to both distant and nearby regions of the early solar system. Among the surprises was the presence of glycine, an amino acid used in proteins. Though not definitive proof of life, its presence raised questions about organic material in space. Stardust showed that comets can carry complex chemistry. It supported theories that some ingredients for life might have come from space. These findings continue to influence astrobiology research. The mission was also notable for its innovative design. The aerogel was a groundbreaking tool for space science. Its transparent, low-density structure minimized impact damage to captured particles. The return capsule's precision landing demonstrated NASA's growing capability in sample return. Stardust set the stage for future missions like OSIRIS-REx. After the sample return, the main spacecraft continued flying. NASA repurposed it for a second mission called Stardust Next. In 2011, it made a flyby of Comet Tempel 1, the same comet targeted by Deep Impact in 2005. This allowed scientists to compare changes in the surface after several years. It was the first time a comet was visited twice by spacecraft. Stardust's dual missions made it one of the most efficient spacecraft ever launched. Its extended lifespan and adaptability showed the value of reusing space assets. Even long after the initial encounter, it continued producing valuable science. The mission eventually ended in 2011 with a final shutdown signal from Earth, but its data lives on in laboratories and archives. The Stardust capsule is now displayed at the Smithsonian National Air and Space Museum. It represents a turning point in planetary science, the first return of solid samples from beyond the Moon. The dust particles continued to be studied with new techniques. They remain among the most pristine extraterrestrial materials ever collected. Public interest in the mission was significant thanks to the dramatic re-entry and sample return. Stardust was also part of the Stardust at Home project, which let people help analyze images of captured particles online. This citizen science effort engaged thousands of volunteers worldwide. It showed how space science can be collaborative and inspiring. Stardust proved that tiny particles can hold enormous stories. It brought back fragments from the building blocks of the solar system, ancient, untouched, and full of clues. The mission opened a new chapter in sample return science. It reminded us that comets are not just icy visitors, they are cosmic archives, still whispering secrets from billions of years ago. Akatsuki, meaning dawn in Japanese, is a Venus climate orbiter launched by JWST in 2010. Its mission is to study the planet's extreme and dynamic atmosphere. Venus, often called Earth's twin in size, is wildly different in climate. Hot enough to melt lead, with crushing pressure and thick clouds of sulfuric acid. Understanding its atmosphere could help us learn about climate systems across the solar system. But Akatsuki's journey was anything but straightforward. After launching successfully, the spacecraft was supposed to enter Venus orbit in December 2010. However, its main engine failed during the critical insertion burn. Akatsuki missed the planet entirely and ended up orbiting the Sun. For most missions, this would have been a total failure, but JWST engineers devised a daring recovery plan using small attitude control thrusters. For 5 years, Akatsuki coasted through interplanetary space. It made gradual course corrections using limited fuel. In December 2015, it approached Venus once again, this time attempting orbital insertion with only backup engines. Against the odds, the maneuver succeeded. Akatsuki entered a highly elliptical orbit, completing one loop around Venus every 10 to 12 days. Despite the initial failure, Akatsuki began a productive science phase. Its instruments include 5 cameras operating at infrared, ultraviolet, and visible wavelengths. These sensors allow scientists to observe cloud layers, wind patterns, and temperature structures. Akatsuki is particularly focused on the middle and upper atmosphere, regions poorly understood before. The orbiter is revealing Venus as a far more active world than previously thought. The spacecraft observed atmospheric superrotation, a phenomenon where winds at the equator whip around the planet faster than Venus itself rotates. These winds can reach 360 kilometers per hour, making Venus's atmosphere one of the most extreme in the solar system. Akatsuki also captured unusual wave patterns in the clouds, including giant bow-shaped structures. These may be linked to mountain ranges far below the dense clouds. In 2016, Akatsuki detected a massive standing gravity wave, a rare atmospheric structure that remained stationary for days. It stretched thousands of kilometers across the planet. Scientists believe it was caused by air rising over highland regions, similar to how mountain waves form on Earth. This discovery helped link surface topography to atmospheric behavior. Akatsuki's instruments have also studied sulfur dioxide concentrations and cloud composition. They suggest rapid vertical mixing and photochemical reactions. The orbiter tracks changes in brightness across different altitudes, helping scientists model Venusian weather. Its infrared sensors offer limited nighttime imaging, offering a rare glimpse into the planet's dark side. These capabilities are crucial for understanding global circulation. The mission aims to answer big questions. Why did Venus become so hostile? What caused its runaway greenhouse effect? Could Earth face a similar fate in the distant future? Akatsuki provides long-term data to explore these questions. It also complements older data from missions like Magellan and Venus Express. Together, they help piece together Venus's climatic evolution. Akatsuki has outlived its original lifespan. JWST extended the mission multiple times as instruments and systems remain functional. The spacecraft continues to send back data from its elongated orbit. Engineers monitor fuel levels and thermal conditions carefully. Despite its limited propulsion, it remains stable and scientifically valuable. The mission marked a comeback for Japan's planetary program. After several high-profile setbacks, Akatsuki's recovery was seen as a triumph of persistence and ingenuity. It boosted JAXA's confidence and reputation globally. The spacecraft became a symbol of resilience, both in engineering and in scientific vision. Akatsuki also serves as a precursor for future Venus exploration. NASA and ESA are planning new orbiters and landers to follow up on its findings. The mysteries of Venus, from its volcanic past to potential microbial life in the clouds, are now back in focus. Akatsuki laid the groundwork for these missions with its long-term observations. Though it may not have landed or returned samples, Akatsuki brought Venus closer than ever through detailed atmospheric monitoring. It revealed a complex, turbulent world hiding beneath thick clouds. Its recovery story is a reminder that success in space often comes from second chances. Sometimes, even when everything seems lost, a mission can still find its way and deliver remarkable science. Voyager 2. Voyager 2 is one of humanity's most ambitious spacecraft, launched by NASA in 1977. Unlike its twin, Voyager 1, this probe followed a unique trajectory that allowed it to visit all 4 gas giants. It remains the only spacecraft to have flown past Uranus and Neptune. These encounters revealed entirely new worlds and expanded our understanding of the outer solar system. The mission continues to operate over 19 billion kilometers from Earth. Voyager 2 first reached Jupiter in 1979, capturing detailed images of the Great Red Spot and Jupiter's faint rings. It also studied the planet's massive magnetosphere and dozens of moons. Then in 1981, it flew past Saturn, providing new views of its rings and atmosphere. After each flyby, engineers reprogrammed the probe for the next planetary encounter. This adaptability was key to the mission's long-term success. In 1986, Voyager 2 became the first and still only spacecraft to fly by Uranus. It revealed the planet tilted sideways with a magnetic field misaligned from its rotation axis. The mission discovered 10 new moons and 2 new rings. It also showed a surprisingly featureless blue-green atmosphere. Despite technical limitations, the data sent back was unprecedented. Then in 1989, Voyager 2 reached Neptune. It flew just 4,950 kilometers above the planet's cloud tops, the closest approach of any planetary flyby. Neptune surprised scientists with dynamic weather, including the fastest winds in the solar system. Voyager 2 discovered the Great Dark Spot and captured images of thin, clumpy rings. The mission also revealed active geysers on Neptune's largest moon, Triton. Voyager 2's planetary tour lasted 12 years, but its mission didn't end there. It continues traveling outward, entering interstellar space in 2018, 6 years after Voyager 1. Now beyond the heliopause, it measures cosmic rays, magnetic fields, and plasma densities. These data are helping scientists understand the boundary between our solar system and the galaxy. It's a rare glimpse into the space between stars. Communication with Voyager 2 is slow and delicate due to its vast distance. Signals take over 18 hours to reach Earth, and the spacecraft uses only 20 watts to transmit data. Engineers have had to manage power carefully as its nuclear battery decays. Instruments are being shut down gradually to extend the mission. Even now, it returns usable science every few days. One of Voyager 2's most famous features is the Golden Record, a time capsule with sounds, music, and greetings from Earth. Designed by a team led by Carl Sagan, it includes messages in 55 languages, whale songs, and images of human life. It's meant to be discovered by intelligent life far in the future. The record represents a poetic farewell from Earth. Voyager 2 has also contributed to heliophysics. It measured solar wind speeds as they weakened with distance. After crossing the termination shock and heliosheath, it entered a region dominated by interstellar plasma. These transitions confirmed models about the structure of the heliosphere. The spacecraft effectively became an interstellar observatory. Despite being built with 1970s technology, Voyager 2 remains one of the most sophisticated long-distance missions ever created. Its resilience comes from redundant systems and clever software updates. NASA's Deep Space Network continues to support the mission. Teams occasionally reconfigure hardware using techniques developed decades after launch. It's a testament to engineering durability. Voyager 2's legacy is enormous. It rewrote the textbooks on Uranus and Neptune. Many of its discoveries remain the only direct data we have about those planets. Its success inspired proposals for future missions to ice giants. Scientists are eager to return to these distant worlds. Voyager 2 remains the pioneer of that path. Public fascination with the Voyagers has only grown over time. Documentaries, books, and podcasts revisit their journey regularly. Their quiet persistence beyond the solar system captures something profound about human curiosity. Few machines have gone so far or lasted so long. Voyager 2 continues to represent the spirit of exploration. As of today, Voyager 2 still listens and speaks, a tiny voice echoing through the void. It carries messages from Earth and memories of planets it once passed. Each signal it sends is a reminder of what humanity can achieve. Even without new images, the science and symbolism of Voyager 2 are as relevant as ever.
Mars Express. Launched in 2003 by the European Space Agency, ESA, Mars Express marked Europe's first successful mission to the Red Planet. Its primary goal was to study the Martian surface, atmosphere, and subsurface. It arrived at Mars in December 2003 and entered a highly elliptical polar orbit. From there, it began surveying the entire planet over successive asses. Its suite of instruments offered new perspectives on Mars's geology and history. One of the most striking discoveries came from the Marsis radar, designed to probe beneath the surface. In 2018, Marsis detected strong reflections consistent with liquid water beneath the South Polar ice cap. This suggested that subglacial lakes might still exist on Mars today. If confirmed, they could represent potential habitats for microbial life. It was a major turning point in the search for water beyond Earth. Mars Express also produced some of the most detailed topographic maps of the planet. Its high-resolution stereo camera, HRSC, imaged canyons, volcanoes, and craters in 3 dimensions. These images revealed tectonic activity and ancient river valleys. The data helped identify regions where water once flowed. It supported the idea that Mars had a complex and dynamic past. The orbiter also carried instruments to study the Martian atmosphere. It measured water vapor, ozone, and dust storms over time. Seasonal changes and atmospheric escape were tracked across years. Mars Express helped identify how the planet lost most of its early atmosphere. This process is key to understanding why Mars became cold and dry. One component of the mission was the Beagle 2 lander, developed in the UK. Unfortunately, it failed to fully deploy after landing. For over a decade, it was presumed lost. But in 2015, NASA's Mars Reconnaissance Orbiter found it intact on the surface, partially unfolded but clearly present. Though the lander failed, the main orbiter has operated successfully for over 20 years. Mars Express continues to function today, making it one of the longest-running Mars missions. Its longevity is due to robust design and careful energy management. Engineers have updated its software multiple times to extend its life.
Even as newer missions arrive, Mars Express provides valuable long-term data. It remains a cornerstone of Mars observation. Its global mapping helped guide the selection of landing sites for future rovers. Regions of high interest like Jezero Crater and Gale Crater were studied in advance. Data from Mars Express helped confirm clay deposits and mineral layers. These features pointed to ancient environments that could once have supported life. It directly influenced subsequent exploration. Its radar sounder has continued to reveal surprises. In addition to the polar lake signals, Mars found evidence of layered ice deposits and buried basins. These underground structures preserve climate history from millions of years ago. By scanning different regions, Mars Express is slowly uncovering the planet's deep past. It shows how radar can complement surface observations. Mars Express has also studied the interaction between solar wind and the Martian atmosphere. It recorded auroras, magnetic anomalies, and charged particle flows. These data help scientists understand how Mars behaves without a global magnetic field. The findings also inform how solar radiation affects habitability on other worlds. It's a window into planetary evolution. The orbiter supports other missions as a communication relay. It has relayed data from rovers and landers back to Earth. This includes NASA missions like Phoenix and Perseverance. ESA designed Mars Express to work with international partners. It shows how collaboration enhances exploration outcomes. Mars Express's success helped pave the way for ESA's future planetary goals. It demonstrated that Europe could build and operate complex missions beyond Earth orbit. The mission's architecture influenced designs for ExoMars and JWST. It also strengthened partnerships with NASA and Russia. The experience gained has had ripple effects across multiple programs. Despite its quiet role compared to rovers, Mars Express remains vital. It orbits silently above a planet still revealing its secrets. With each pass, it adds layers of understanding to Mars' story. It may not drill or drive, but from its high perch, it sees the big picture and helps us see it too. OSO-8. Launched in 1975, OSO-8 was the final satellite in NASA's orbiting Solar Observatory series. These missions were designed to observe the Sun in wavelengths that cannot be seen from Earth's surface. OSO-8 focused on ultraviolet and X-ray radiation, shedding light on the Sun's high-energy behavior. Operating for over 3 years, it offered a rare view into the outer layers of the solar atmosphere. Its data helped shape modern solar physics. The satellite had a unique, spinning, stabilized design. A rotating section provided stability, while a sun-pointing platform housed instruments. This ensured precise solar alignment for continuous data collection. OSO-8 carried spectrometers, photometers, and detectors sensitive to various wavelengths. The mission's instruments were more advanced than those on previous OSOs. One of OSO-8's major contributions was its observation of solar flares. These explosive events release enormous energy in ultraviolet and X-ray bands. The satellite recorded detailed flare spectra, helping scientists understand their thermal and non-thermal components. This data improved models of solar magnetic activity. It also informed predictions of space weather that can affect satellites and power grids. OSO-8 also studied the quiet sun between flare events. It analyzed ultraviolet emissions from the chromosphere and corona. These observations revealed temperature gradients and ionization states in solar plasma. They helped establish a clearer picture of how energy moves through the sun's outer layers. Even small fluctuations provided insights into solar dynamics. Another key focus was coronal heating, the mysterious process that raises the corona's temperature above 1 million degrees Celsius. OSO-8's ultraviolet and X-ray data contributed to the theory that magnetic waves and reconnection events play a role. These observations laid groundwork for future missions like SOHO and Parker Solar Probe. OSO-8 helped define the right questions. The satellite also investigated solar irradiance, the total energy the Sun emits toward Earth. OSO-8 measured changes across ultraviolet wavelengths. This information was vital for understanding how solar activity affects Earth's upper atmosphere. Variations in UV radiation influenced the ionosphere, impacting communications and satellite orbits. OSO-8 provided real-time monitoring during a period of high solar activity. OSO-8's instruments had excellent temporal resolution. This allowed researchers to study how solar phenomena evolve on minute-by-minute scales. Observations of flare rise times, decay patterns, and energy spectra became important for refining theoretical models. It was a step forward in linking observations to physical mechanisms. OSO-8 bridged a gap between theory and data. Although the mission ended in 1978, OSO-8's datasets remain valuable. They serve as historical benchmarks for comparing long-term solar activity. Solar scientists often revisit OSO-era data to validate trends seen in modern missions. Its observations also inform simulations of solar-terrestrial interactions. The legacy of OSO-8 continues to support current research. The mission also demonstrated technical advances in satellite design. It used improved thermal control, power systems, and optical pointing technologies. These features allowed OSO-8 to achieve higher precision and longer operational life than its predecessors. The satellite performed reliably despite the harsh conditions of space. Its success informed the design of future solar observatories. OSO-8 was not a headline-grabbing mission, but it quietly changed the field. It provided continuous solar data during an era of limited space assets. Its findings influenced solar flare theory, space weather prediction, and our understanding of solar variability. Many results from OSO-8 were published in foundational papers of solar physics. The mission showed that observing the Sun requires long-term commitment. Solar cycles last 11 years, and missions like OSO-8 help build the timeline. Even short missions can anchor decades of research. OSO-8 reminded us that space science isn't always about distant planets. Sometimes it's about staring straight into our own star, and doing it carefully. From a historical perspective, OSO-8 marks the transition to a new era. It connected early satellite efforts to the more sophisticated observatories that followed. While technology advanced, the questions OSO-8 helped pose remain central today. Its role may be overlooked, but its contributions are deeply embedded in solar science. Ulysses was a joint mission between NASA and ESA, launched in 1990 with a bold goal: to study the Sun's poles. Most solar observatories orbit near the ecliptic, seeing the Sun's equator. But Ulysses needed a polar view to understand the Sun's three-dimensional structure. To do this, it had to leave the plane of the solar system, an unprecedented maneuver. The mission required both creativity and cooperation. The spacecraft took an unusual route to get there. It used a gravity assist from Jupiter in 1992 to swing into a high-inclination solar orbit. This maneuver bent its path nearly 80 degrees above the Sun's equator. It marked the first time a spacecraft studied the solar poles directly. Ulysses went on to complete 3 solar orbits over nearly 19 years. Ulysses wasn't equipped with cameras. Instead, it carried magnetometers, plasma sensors, and particle detectors. Its focus was on fields, winds, and charged particles. These tools allowed it to study the solar wind's variation across latitudes. It helped identify differences between the fast polar wind and the slower equatorial outflow. Ulysses expanded our understanding of the Sun's heliosphere. One key discovery was that solar wind from the poles is more uniform and faster than expected. During solar minimum, this fast wind dominates the heliosphere. Ulysses observed how this pattern changed as solar activity rose. It provided real data to replace assumptions about solar wind distribution. The findings had implications for space weather and interplanetary travel. The spacecraft also studied the interstellar medium, the space beyond the Sun's influence. As Ulysses moved far from Earth, it sampled cosmic rays and interstellar dust. These measurements informed models of how the solar system interacts with the galaxy. Ulysses helped define the boundaries of the Sun's magnetic influence. Magnetic field data from Ulysses offered insight into the solar dynamo, the process generating the Sun's magnetic field. By comparing polar and equatorial data, scientists refined theories about magnetic cycle evolution. The probe captured changes as the Sun flipped polarity around solar maximum. Ulysses made it possible to study the Sun's behavior as a global system. Ulysses flew through the solar poles during both quiet and active solar conditions. It monitored coronal mass ejections, CMEs, solar flares, and energetic particles. This long-term dataset was vital for understanding solar variability. It was one of the only missions to study how polar regions contribute to overall solar dynamics. Because it carried no imaging system, Ulysses was often overlooked in public media. But among scientists, it was recognized as a milestone. It produced over 1,000 peer-reviewed papers. Its data were used in models of solar wind acceleration, galactic cosmic ray shielding, and space mission planning. It became a workhorse of solar science. The spacecraft's endurance was remarkable. It operated far beyond its original 5-year plan, finally shutting down in 2009. Engineers overcame technical issues with dwindling power and aging hardware. Ulysses communicated via the Deep Space Network even as its systems faded. Its longevity allowed it to observe nearly 2 full solar cycles. The mission also highlighted the value of international collaboration. NASA provided the spacecraft and launch, while ESA contributed the instruments and management. This partnership demonstrated how agencies could share risks and expertise. Ulysses became a model for later joint missions like Solar Orbiter. It showed how science benefits from global cooperation. The polar orbit of Ulysses remains unique to this day. No other mission has revisited those regions with such detail. Plans for future solar polar observatories are now in development, but Ulysses will always be the first to have glimpsed the Sun's high latitudes. Its path remains unmatched in the history of solar exploration. Although it traveled far from public attention, Ulysses redefined how we see the Sun. It proved that solar science isn't just about looking at the surface, it's about understanding the invisible flows of energy, particles, and fields. Ulysses showed us that even without pictures, a mission can reveal profound truths hidden in plasma and magnetism. SMART-1 was a European Space Agency (ESA) mission designed to test new space technologies on a journey to the Moon. Launched in 2003, it was the first European spacecraft to orbit the Moon. The SMART in its name stood for Small Missions for Advanced Research in Technology. At only 367 kilograms, SMART-1 was lightweight and relatively low cost. But its mission carried major technological and scientific goals. Its most notable innovation was its propulsion system. SMART-1 used a solar electric ion engine, a method that expels ions to produce thrust. Unlike chemical rockets, ion engines are incredibly efficient but provide very low force. Over many months, SMART-1 spiraled gradually outward from Earth's orbit. It eventually reached lunar orbit in 2004, demonstrating ion propulsion for deep space travel. The engine operated for more than 5,000 hours, setting records at the time. Engineers monitored how it performed under different conditions and orbital maneuvers. It proved to be reliable and controllable. Ion propulsion had been tested before, but SMART-1 was the first mission to use it for reaching another celestial body. The mission became a case study in low-thrust trajectory design. Besides its engineering goals, SMART-1 carried a suite of scientific instruments. These included cameras and spectrometers to study lunar surface composition. It focused on identifying minerals such as calcium, magnesium, and aluminum. The data helped scientists understand how the Moon's crust formed and evolved. It also aimed to locate signs of water ice in permanently shadowed craters. One of its instruments, AMIE, Advanced Moon Imaging Experiment, captured hundreds of images of the lunar surface. These included views of craters, volcanic plains, and polar regions. The camera was compact but capable, delivering sharp images of targeted regions. The mission mapped potential landing sites for future lunar landers. It also provided high-resolution views of unexplored areas. Another major objective was to observe Earth and the Moon together. From its orbit, SMART-1 conducted joint observations of both bodies. It tested how spacecraft might monitor planetary environments remotely. These experiments contributed to Earth-Moon system models. They also helped prepare techniques for future planetary missions. SMART-1's orbit was highly elliptical, allowing it to fly low over different parts of the Moon. This provided varied lighting angles and altitudes for its instruments. It enabled imaging during both day and night conditions. The data gathered across these passes offered diverse perspectives on lunar terrain. This flexible orbit strategy was part of the mission's experimental approach. Although SMART-1 was small, it had a big impact on lunar science. It confirmed that Europe could design, launch, and operate planetary missions independently. The mission laid a foundation for ESA's later contributions to programs like Artemis and Lunar Gateway. It also advanced understanding of how small spacecraft can achieve complex goals. The mission ended in 2006 with a planned impact on the Moon's surface. The crash site was chosen carefully to maximize observation opportunities. Ground-based telescopes and orbiters watched the plume from the impact. This offered additional data on surface composition. Even in its final moments, SMART-1 was producing useful science. One of the mission's legacies was its emphasis on doing more with less. With limited mass and budget, it achieved meaningful results. It also proved that technology demonstration missions could offer valuable science. SMART-1 became a model for small, targeted missions in planetary exploration. Its influence extended to both ESA and other space agencies. The mission also helped popularize ion propulsion beyond engineering circles. It showed that slow and steady could win the race to the Moon. This idea has since become common in mission planning. Today, ion drives are used on many spacecraft, including ESA's Bepi-Colombo and NASA's Dawn. SMART 1 helped validate this shift in thinking. Though often overlooked in the shadow of larger missions, SMART 1 showed the power of efficient, well-planned innovation. It reached the Moon, tested key systems, and expanded Europe's role in planetary science. SMART 1's story is one of quiet determination, a reminder that big discoveries often ride aboard small spacecraft. WISE. NASA's WISE mission, or the Wide Field Infrared Survey Explorer, launched in December 2009 to map the entire sky in infrared light. Unlike visible light telescopes, WISE could detect heat emitted by cold or hidden objects. Its primary goal was to discover and catalog objects that optical telescopes couldn't see. WISE completed its main survey in just 10 months, but its data continues to shape modern astronomy. The spacecraft used 4 infrared detectors cooled to extremely low temperatures. These allowed it to spot faint, distant, or cold celestial bodies. WISE scanned the sky in strips, building a comprehensive infrared map. It captured hundreds of images each day and compiled data on hundreds of millions of objects. The scale and sensitivity of the mission were unprecedented. Among its most important discoveries were brown dwarfs, objects too big to be planets, but too small to be stars. WISE found hundreds of these elusive bodies, including some of the coldest ever observed. One, named WISE 0855-0714, is only a few light-years away and colder than the freezing point of water. These objects help fill gaps in our understanding of star and planet formation. WISE also surveyed the asteroid population in our solar system. It discovered tens of thousands of new asteroids, including some classified as potentially hazardous. The mission provided key data on their size, shape, and composition. It improved our planetary defense models and contributed to the Near-Earth Object database. Some asteroids observed by WISE are now targets for future missions. In deep space, WISE discovered entire galaxies previously unknown. Many were obscured by dust and invisible in optical wavelength. The mission revealed infrared luminous galaxies forming stars at furious rates. Some were among the most energetic systems in the universe. WISE's catalog changed how astronomers viewed galaxy evolution and star formation history. The mission also detected comets and icy bodies in the outer solar system. It measured their thermal emissions and traced their orbits. These observations helped classify cometary families and activity cycles. WISE offered insight into the colder, more distant regions of our system. Its broad sensitivity made it a multi-purpose observatory. After completing its primary mission, WISE was put into hibernation in 2011, but in 2013, NASA reactivated the spacecraft for a new role, hunting near-Earth asteroids. This extended mission, called NEO-WISE, continues today. It has discovered thousands of new near-Earth objects and tracks known ones with better precision. The spacecraft still works well despite years in space. The data were made public and remain widely used. Astronomers continued to mine WISE catalogs for new discoveries. It supports research in fields from cosmology to planetary science. WISE data are often combined with data from other telescopes like Spitzer and Hubble. Its legacy extends across a broad scientific spectrum. One of WISE's strengths was its ability to survey the entire sky multiple times. This repetition allowed astronomers to detect motion and brightness changes. Variable stars, fast-moving asteroids, and transient phenomena could be tracked. The time-domain dimension added a new layer of discovery. It made WISE not just a catalog, but a dynamic observatory. WISE's influence extended into public imagination as well. Its discoveries of failed stars and hidden galaxies inspired media stories and planetarium shows. The mission's infrared views of nebulae and galaxies are among the most visually striking in astronomy. They show a hidden universe glowing in thermal light. WISE helped popularize the idea of seeing space beyond what eyes can detect. Its compact, efficient design made it an example of what medium-class missions can achieve. It combined robust engineering with focused science goals. The mission met and far exceeded its original objectives. Even today, WISE data are essential for planning future infrared missions like the Nancy Grace Roman Space Telescope. It proved that a single spacecraft can open entire new windows on the cosmos. WISE didn't just reveal new objects, it changed the map of the universe. It gave us a clearer view of what lies behind the dust, beyond the visible. Millions of hidden worlds and cosmic structures came into view. Through its lens, the dark parts of the universe lit up, offering a reminder there's always more to see if we know how to look. Genesis. The Genesis mission, launched by NASA in 2001, had a singular goal: to collect pristine samples of the solar wind. These charged particles, ejected from the Sun, carry information about the solar system's original composition. By capturing and returning them to Earth, scientists hoped to unlock secrets about planetary formation. Genesis was the first mission to bring solar material back home. It aimed to provide a direct look at our cosmic origins. To collect the solar wind, Genesis used ultra-pure collectors made of diamond, sapphire, gold, and silicon. These wafers were arranged like flower petals, catching particles that impacted at high speeds. The spacecraft parked itself at the L1 Lagrange point, about 1.5 million kilometers from Earth. There it basked in the constant stream of solar particles. This location ensured uninterrupted exposure to the solar wind. Genesis remained in this position for over 2 years, gathering ions from different types of solar wind. The collectors were periodically rotated to optimize exposure and categorize particle streams. Scientists were particularly interested in isotopes of oxygen, nitrogen, and noble gases. These elements act as fingerprints of the early solar nebula. The data could help resolve long-standing questions about how planets and moons formed. After gathering its samples, Genesis headed back to Earth in 2004. The return capsule was designed to deploy a parachute and be caught mid-air by helicopters, but a sensor was installed backward and the parachute failed to open. The capsule crashed into the Utah desert at high speed. Many of the delicate wafers shattered on impact, and the mission faced serious setbacks. Despite the crash, recovery efforts salvaged valuable material. Scientists retrieved fragments of the collectors and began analyzing what remained. Thanks to cleanroom-level handling and advanced recovery methods, the contamination was limited. The samples were still viable for high-precision lab analysis. It turned into a story of scientific resilience and adaptation. Genesis provided the most accurate measurements to date of oxygen isotopes in solar material. The results showed that the Sun's composition differs slightly from that of Earth and other solar system bodies. This unexpected discovery suggested that local processes in the early solar nebula altered material before planets formed. It was a key finding in understanding planetary differentiation. The mission also measured isotopes of nitrogen and noble gases with unprecedented precision. These data challenged prevailing models of solar system evolution. They offered new constraints on theories about the Sun's formation and early solar dynamics. Genesis revealed that even tiny differences in elemental ratios have enormous implications. The mission opened a new chapter in cosmochemistry. Genesis' use of passive collection materials was an engineering milestone. The need for extreme purity and stability pushed materials science to new limits. The collectors had to remain uncontaminated while facing high-velocity impacts. Innovations from the mission are now applied in other sample return programs. Genesis helped refine the art of capturing the invisible. The mission's accident also triggered a re-evaluation of spacecraft sensor protocols. NASA implemented stricter testing and review systems for future missions. Lessons from Genesis improved the design of later sample return missions like OSIRIS-REx. It became a turning point in how risk and redundancy are handled in spacecraft recovery. Genesis left a procedural legacy as well as a scientific one. Despite its rocky return, Genesis was scientifically successful. Its samples continue to yield results years after landing. The mission showed that even damaged data can transform our understanding of the cosmos. Perseverance in the face of failure became part of its legacy. The name Genesis gained new meaning as a symbol of renewal. Researchers around the world still study Genesis samples today. The mission's archives are a resource for future technologies and scientific tools. As analytical instruments improve, new insights emerge from old particles. The mission set a standard for interdisciplinary collaboration in planetary science. It remains a landmark in space sample return history. Genesis reminded us that the building blocks of planets are still floating between us and the Sun. By reaching out and catching them, we gain access to the story of our beginning. And while the mission's return didn't go as planned, its contribution to science was undeniable. In tracing the Sun's breath, Genesis gave voice to the silence of deep time.
Shoemaker, launched in 1996, was the first spacecraft to orbit and then land on an asteroid. Its target was 433 IRAS, a 34-kilometer-long near-Earth asteroid shaped like a peanut. The mission was part of NASA's Discovery program, focused on low-cost, high-impact planetary exploration. NEAR stood for Near-Earth Asteroid Rendezvous. The spacecraft was later renamed in honor of planetary scientist Eugene Shoemaker. After launch, Shoemaker performed an Earth flyby to adjust its trajectory. It encountered IRAS in 1998 but had to delay orbit due to a navigation glitch. It finally entered orbit around IRAS in February 2000. This marked the first time a spacecraft orbited a small celestial body. The mission delivered detailed maps and data on the asteroid's surface and composition. Shoemaker carried instruments including a multispectral imager, X-ray and gamma-ray spectrometers, a magnetometer, and a laser rangefinder. These tools enabled precise surface mapping and mineral analysis. NEAR revealed that IRAS is a solid body, not a loose collection of rubble. It showed signs of past collisions and ancient craters. The spacecraft observed thousands of boulders, grooves, and ridges on IRAS. Some features suggested seismic activity from impacts. These details helped scientists understand the mechanical properties of small bodies. Shoemaker provided a window into the early solar system. IRAS is thought to be a relic from the system's formation over 4.5 billion years ago. The mission gradually lowered its orbit, flying as close as 5 kilometers above the surface. It collected over 160,000 images, creating an unprecedented visual archive. These data allowed 3D modeling of the entire asteroid. Scientists studied surface aging processes and compared IRAS to meteorites found on Earth. NEAR became a key reference for asteroid science. The most surprising moment came in February 2001, when NASA decided to attempt a landing. Although the spacecraft had no landing gear, engineers plotted a descent to IRAS's surface. Using only its thrusters, NEAR gently touched down at about 1.5 meters per second. It became the first spacecraft to land on an asteroid, even though it wasn't designed to. Remarkably, NEAR survived the landing and kept communicating.
From the surface, it transmitted data for over 2 weeks. Its instruments gathered additional readings on gamma-ray emissions. This added a new layer to our understanding of surface composition. The extended mission exceeded all expectations and demonstrated the spacecraft's resilience. The landing proved that precise navigation around small bodies was possible. It also showed that soft touchdowns on asteroids could yield scientific rewards. These lessons would shape future missions like OSIRIS-REx and Hayabusa. Near Shoemaker established critical groundwork for asteroid exploration and sample return planning. The mission also addressed broader planetary defense goals. By studying IRAS's structure and orbit, NEAR helped assess asteroid impact risks. It showed how we might analyze a potential threat in detail. This work continues today in the context of missions like DART. NEAR laid the foundation for turning science into strategy. The success of NEAR Shoemaker inspired both scientists and the public. It demonstrated that small, focused missions could achieve historic feats. The imagery and data from IRAS became part of educational programs worldwide. NEAR helped raise awareness of asteroid science as a frontier worth exploring. It brought the space rock into cultural view. The spacecraft systems performed exceptionally well throughout its mission. Its efficient design and operational discipline kept costs low. NEAR proved that advanced science didn't always require massive budgets. It stood as a model for how space agencies could do more with less. The mission's results far exceeded expectations. Long after its final transmission, NEAR Shoemaker remains on the surface of IRAS, a silent monument to one of space exploration's boldest decisions. It turned a navigation challenge into a pioneering achievement. And it remains there today, a spacecraft resting on a rock, drifting quietly through interplanetary space.
Pioneer Venus Multiprobe. The Pioneer Venus Multiprobe mission, launched by NASA in 1978, was designed to explore the mysterious atmosphere of Venus. While most missions focus on orbiting or landing, this one took a different approach. It dropped 4 separate atmospheric probes into Venus's dense and hostile skies. Each probe was equipped to sample gases, measure pressure, and observe cloud layers. The mission aimed to study Venus's structure all the way down to its surface. One of the major challenges was surviving Venus's extreme environment. Temperatures exceed 460 degrees Celsius, and the atmospheric pressure is over 90 times that of Earth. The atmosphere is composed mostly of carbon dioxide, with clouds of sulfuric acid. No spacecraft could operate for long under those conditions, so the probes were built to collect as much data as possible during their descent. The spacecraft carried 1 large probe and 3 smaller ones, each sent to different parts of the planet. They were released while the main spacecraft was still approaching Venus. Each followed a different trajectory to sample a wide range of atmospheric conditions. The plan was to compare the data from different locations to understand Venus's global climate. This distributed approach was a first in planetary exploration. The large probe entered the atmosphere on December 9, 1978. It survived for about an hour, collecting data on temperature, winds, and chemical composition. The smaller probes had no parachutes and fell faster, but one of them exceeded expectations. The day probe continued to transmit even after hitting the surface. It became one of the few human-made objects to survive briefly on Venus. The data revealed a complex and multi-layered atmosphere. Temperatures and pressures varied in unexpected ways as the probes descended. The probes detected thick cloud decks composed of sulfuric acid droplets. Lightning and wind activity were also observed. These insights dramatically improved models of Venusian weather and climate dynamics. The mission confirmed that Venus's thick atmosphere traps heat through a runaway greenhouse effect.
It showed that the lower atmosphere is extremely stable and stratified. Carbon monoxide and sulfur dioxide were found in significant quantities. This suggested active chemical processes, possibly driven by volcanic activity. Venus's hellish conditions were more clearly defined than ever before. The measurements from the 3 small probes provided crucial comparisons. They showed that conditions on Venus varied depending on location and altitude. The night probe, for example, found different wind patterns compared to the others. These differences helped scientists refine general circulation models. It was an early success in atmospheric field sampling beyond Earth. The Multiprobe bus itself also collected data during its descent. It was not expected to survive long, but contributed valuable measurements. Its sensors monitored particle flux, magnetic fields, and solar wind interaction. This helped characterize Venus's upper atmosphere and ionosphere. It gave context to the data collected by the entry probes. Pioneer Venus Multiprobe was a technological and scientific milestone. It demonstrated that atmospheric entry science could be done affordably and efficiently. The probes were relatively simple but provided high-quality data. Their performance influenced later missions, including Galileo's probe into Jupiter's atmosphere. It became a model for targeted atmospheric studies. The mission proved that even short-lived probes can yield deep scientific value. By sampling multiple points in the atmosphere simultaneously, scientists gained a more complete picture. This approach has since been adopted in studying Earth's own weather systems. Venus served as a proving ground for methods that later came back home. The Multiprobe mission also raised new questions. Where does the sulfur in the atmosphere originate? What causes the superrotation of Venus's upper winds? Why is there such a stark difference between the day and night sides? These puzzles continue to drive Venus science. The mission's data remain a foundation for future exploration. Today, Pioneer Venus Multiprobe is remembered as a daring and unconventional mission. It didn't aim for orbit or landing, but instead plunged into the unknown. Its legacy lies in how it redefined atmospheric science beyond Earth. The probes may be gone, but their data still echo through research papers and planetary models.
IRAS, Infrared Astronomical Satellite. Launched in 1983, IRAS was the first satellite to perform a full-sky survey in infrared. It marked a turning point in observational astronomy by opening a new window on the universe. Unlike visible light, infrared reveals objects that are cold, dusty, or hidden behind gas clouds. IRAS discovered hundreds of thousands of new astronomical sources. It transformed our understanding of the cosmos. The satellite was a joint project between the United States, the Netherlands, and the United Kingdom. It carried a 57-centimeter telescope cooled to cryogenic temperatures. Liquid helium kept its instruments cold enough to detect faint heat signals. This allowed it to observe regions of the universe invisible to optical telescopes. The mission lasted only 10 months, but produced decades' worth of data. IRAS scanned the sky in 4 infrared bands, from 12 to 100 microns. It mapped about 96% of the celestial sphere during its operational life. The resulting catalog included stars, galaxies, nebulae, and other cosmic structures. Many of these objects had never been seen before. IRAS revealed the cool universe for the first time. One of its key discoveries was a new class of galaxies called ultraluminous infrared galaxies, or ULIRGs. These systems emit most of their energy in the infrared and are often sites of intense star formation. IRAS showed that the early universe was full of dusty, active galaxies. This reshaped theories of galaxy evolution and starburst activity. IRAS also discovered several previously unknown comets. Among them was comet IRAS-Araki-Alcock,
which made a close pass by Earth in 1983. The satellite detected the comet's infrared glow as it approached. IRAS helped track its size, shape, and dust production. This showed how infrared could support solar system studies as well. Closer to home, IRAS observed debris disks around young stars. These disks are believed to be the early stages of planetary formation. The most famous case was the discovery of a disk around Vega, a bright star visible from Earth. This was a direct hint at planetary systems forming beyond our own. It inspired later missions to search for exoplanets. The satellite also helped study the structure of our own Milky Way galaxy. It traced the distribution of cold dust along the galactic plane. These data revealed complex filaments and star-forming regions. IRAS gave astronomers a better grasp of where and how stars are born. It linked cold interstellar material to the cycle of stellar evolution. Although IRAS was never intended to last long, its impact was massive. The mission ended when it ran out of coolant, as expected, but the data archive continued to be used for decades. Researchers reanalyzed the data with new algorithms and combined it with later surveys. IRAS became a foundational data set for infrared astronomy. Technologically, IRAS demonstrated that space-based infrared observation was viable and valuable. It proved that Earth's atmosphere blocks much of the infrared spectrum. Space telescopes would therefore be essential for studying heat-based phenomena. IRAS paved the way for later missions like Spitzer, Herschel, and JWST. The mission also sparked public interest in hidden cosmic structures. Images of dusty nebulae and glowing galaxies captured imaginations worldwide. IRAS brought new aesthetics to astronomy, the universe not in starlight, but in warmth. Its images suggested that even in darkness, the cosmos is alive and dynamic. In terms of raw scientific output, IRAS was one of the most productive missions of its time. Its all-sky survey became a benchmark for future missions. It also revealed how much of the universe lies outside the optical range. This changed telescope design and observing priorities for decades to come. Though its life was short, IRAS left a long legacy. It showed that with the right tools, we could uncover what lies beneath the visible. It helped us see the hidden scaffolding of the cosmos: cold clouds, dust-shrouded stars, and ancient galaxies. And in doing so, it expanded not just our vision, but our sense of the universe itself.
Cluster 2. Cluster 2 is a European Space Agency mission consisting of 4 identical spacecraft flying in formation. Launched in 2000, its purpose is to study Earth's magnetosphere in 3 dimensions. Most previous missions used single satellites, providing only local data. Cluster's configuration allowed scientists to observe spatial variations in magnetic and plasma activity. It became a cornerstone in the study of space weather. The magnetosphere is the region around Earth dominated by our planet's magnetic field. It protects us from solar wind and cosmic radiation. But this shield isn't static. It shifts, pulses, and reconnects. Cluster's 4 spacecraft could track how magnetic structures evolve over time. This real-time 3D insight was a technological leap forward. The satellites fly in a tetrahedral formation, allowing them to triangulate electromagnetic activity. They orbit Earth in highly elliptical paths, reaching up to 124,000 kilometers away. This lets them cross key magnetospheric regions, including the bow shock, magnetotail, and cusp. Each satellite carries a suite of instruments to monitor particles, fields, and waves. Together, they form a dynamic sensor array. Cluster revealed how the solar wind distorts Earth's magnetosphere. When solar storms hit, the bow shock compresses and magnetic reconnection occurs. This releases energy that can cause auroras and disrupt satellites.
Cluster tracked these changes with unprecedented resolution. It provided clues about the timing and triggers of space weather events. The mission also studied magnetic reconnection, a phenomenon where magnetic field lines break and reconnect. This process releases energy explosively, like in solar flares and auroral substorms. By observing reconnection from multiple angles, Cluster tested key physics theories. It helped validate computer models of plasma dynamics. Cluster's data improved our understanding of geomagnetic storms. These storms can disable satellites, disrupt GPS, and damage power grids. By mapping how energy flows through the magnetosphere, Cluster contributed to predictive tools. Its results were shared with meteorological agencies and space operators. It turned abstract science into practical forecasting. One breakthrough was detecting small-scale structures in plasma flows. These included turbulence, eddies, and rapid changes in particle density. Such fine details had been invisible to single satellite missions. Cluster revealed the complexity of interactions between solar and terrestrial magnetic fields. It deepened our picture of the near-Earth space environment. Cluster 2 also collaborated with ground-based instruments and other satellites. This allowed cross-verification of events seen from space and Earth. Auroras observed by cameras on the ground matched plasma activity seen by Cluster. The mission built a bridge between space physics and geophysical research. It showed how local phenomena connect to cosmic forces. Each satellite in the Cluster fleet was built to be identical, but slight variations occurred over time. These differences actually enhanced the mission by allowing subtle cross-calibration. Engineers used them to detect instrument drift and refine data accuracy. The result was a high-precision dataset covering more than 2 decades. Originally planned to last 2 years, Cluster 2 has been repeatedly extended. It remains operational well into the 2020s, far exceeding expectations. Its longevity provided a long-term view of solar cycles and magnetospheric evolution. Cluster became one of the longest-running multi-satellite missions in space history. Its durability is part of its success story. The impact extends beyond space physics. Cluster demonstrated the value of coordinated satellite swarms. This concept is now used in climate science, Earth observation, and even future planetary missions. The ability to capture spatial dynamics in real time opened new scientific frontiers. Cluster was a precursor to swarm-based exploration. Cluster 2 continues to orbit Earth, observing the invisible dance between our planet and the Sun. Its fourfold gaze captures the magnetosphere's rhythms, disruptions, and recoveries. In doing so, it helps protect the technology we rely on and the astronauts we send into orbit. It's a quiet sentinel watching over the magnetic pulse of our world. Helios 1 and 2 were twin spacecraft launched in the 1970s by NASA and West Germany to study the Sun up close. At the time, they became the closest man-made objects to the Sun. Their highly elliptical orbits brought them within 0.3 astronomical units, closer than Mercury. They provided groundbreaking data on solar particles, radiation, and magnetic fields. These were among the earliest missions to explore the inner solar system in detail. Helios 1 launched in 1974, followed by Helios 2 in 1976. Each spacecraft was spin-stabilized and built to withstand intense solar radiation. Their instruments included magnetometers, plasma detectors, and cosmic ray sensors. Despite being over 40 years old, their measurements remain part of foundational solar physics. They helped shape our understanding of solar-terrestrial relationships. The primary goal was to study the solar wind, the stream of charged particles emitted by the Sun. Helios measured its speed, density, temperature, and fluctuations. It detected shock waves traveling through the solar wind and tracked their interactions with planetary fields. These were crucial for understanding space weather. They showed how solar output affects the entire heliosphere. Helios also studied solar flares and coronal mass ejections. These are explosive events that release bursts of radiation and particles. By being so close to the source, Helios could detect their onset more directly than Earth-orbiting satellites. This helped refine models of solar activity and flare prediction. The data supported early warning systems for radiation storms. The spacecraft orbited the Sun in paths tilted slightly from the ecliptic. This allowed them to observe solar phenomena from different angles. They also crossed regions near Mercury's orbit, gathering comparative data. Though not equipped with cameras, their sensors captured electromagnetic and particle behavior in fine detail. This information is still mined by researchers today. Helios missions contributed to our understanding of the Sun's magnetic field. They revealed how it twists into a spiral shape as it moves through space. This structure, known as the Parker spiral, affects how solar particles travel. Helios mapped its geometry and fluctuations over time. These insights fed into models of the heliospheric current sheet. Another major finding was the variation in solar wind properties based on distance and direction. Helios showed that fast and slow solar wind streams have distinct origins. It found that the solar wind accelerates faster near the poles and fluctuates near active regions. These details helped complete the solar wind puzzle. They explained phenomena seen farther out in space. The spacecraft also made observations of interplanetary dust. This material, left over from comets and asteroids, orbits the Sun and affects light transmission. Helios tracked how this dust behaved near the solar furnace. It recorded changes in particle density and composition. These findings were used to understand the inner solar system's material environment. Helios missions also served as thermal engineering tests. The extreme heat and radiation near the Sun were major technical hurdles. The spacecraft used reflective surfaces and thermal shielding to survive. Lessons from Helios informed later missions like Parker Solar Probe and Solar Orbiter. It showed that close solar observation was possible with smart design. Helios 2, in particular, reached a record proximity to the Sun for its time. It approached to within 43 million kilometers, a record that stood for decades. Both missions operated far beyond their expected lifespans. They continued to transmit valuable data well into the 1980s. Their longevity made them cost-effective pioneers. Though their technology is now outdated, their scientific legacy remains current. Data from Helios are still cited in contemporary solar physics. They form a baseline for comparing new findings. Modern missions often validate or expand upon Helios's discoveries. Its raw measurements continue to support peer-reviewed studies. Helios 1 and Helios 2 remain in orbit around the Sun to this day. Silent, ancient, and still circling the star they helped unveil. They are among the first human-made objects to truly enter the inner sanctum of the solar system. Their journey marked the beginning of a long, ever-deepening conversation with our star.
Rosat. Röntgen satellite was a German-led mission launched in 1990 to map the sky in X-rays. Unlike visible light, X-rays come from extreme cosmic environments, black holes, neutron stars, and hot gas clouds. Earth's atmosphere blocks these rays, so space telescopes are essential. Rosat conducted the first all-sky survey in soft X-ray wavelengths. Its observations transformed high-energy astrophysics. The satellite operated for over 8 years, far exceeding its original design life. During this time, it cataloged over 150,000 X-ray sources. These included supernova remnants, galaxy clusters, and distant quasars. Rosat made the invisible universe visible in a new way. It showed that high-energy radiation is everywhere. Rosat's main instruments were a Wolter-type X-ray telescope and 2 detectors, a position-sensitive proportional counter, and a high-resolution imager. It also carried a wide-field camera for extreme ultraviolet observations. This combination gave it versatility across energy ranges. Rosat could observe both bright and faint objects with precision.
One of its biggest contributions was mapping the hot gas that fills galaxy clusters. These X-rays revealed the large-scale structure of the universe. Rosat showed that clusters are interconnected by filaments of heated matter. This supported the idea of a cosmic web, a framework of dark matter and hot gas. It provided direct observational evidence of this hidden scaffolding. Rosat also identified many isolated neutron stars, dense stellar remnants with powerful magnetic fields. These stars often appear as faint X-ray sources without visible light. Before Rosat, only a few were known. Its data expanded the sample size dramatically. This allowed more detailed studies of their cooling rates and internal structures. The satellite played a crucial role in locating supermassive black holes. Many active galactic nuclei emit strongly in X-rays. Rosat helped pinpoint their positions for follow-up with optical telescopes. It also revealed flaring activity and variable sources. These findings were essential for understanding how black holes influence galaxy evolution. Rosat's data improved the safety of future X-ray missions. By mapping the sky's diffuse background, it helped calibrate other detectors. It showed where high-energy radiation might contaminate sensitive instruments. This contributed to the design of later observatories, like Chandra and XMM Newton. Rosat became a reference mission for X-ray astronomy. The mission also had public impact. Its all-sky images were used in education and outreach. People could see the sky not as dots of light, but as glowing clouds of energy. It shifted the public's perception of the cosmos. Rosat's data became a visual gateway to the extreme universe. Rosat wasn't limited to deep space. It also observed our solar system in X-rays. It studied comets and planetary atmospheres in X-rays. These detections were unexpected and opened new questions. How do solar wind particles interact with neutral gases? Rosat showed that X-ray astronomy could extend to planetary science. Toward the end of its life, Rosat switched to targeted observations. It followed up on discoveries from its survey and studied time-variable sources. It tracked X-ray binaries, pulsars, and flare stars. This shift allowed scientists to explore short-term cosmic events. Rosat evolved from mapper to monitor. After operating from 1990 to 1999, Rosat was decommissioned and re-entered Earth's atmosphere in 2011. Some fragments survived and landed in the Bay of Bengal. Despite this dramatic end, its scientific legacy endures. Its catalog remains a key reference for astronomers. Rosat's maps still guide telescopes across the X-ray sky. Rosat opened a new chapter in astrophysics by revealing the universe's hidden violence. It showed that beyond the calm of starlight lies a realm of heat, shock, and collapse. Its success helped legitimize high-energy astronomy as a field. Rosat didn't just see the stars, it saw their ghosts, explosions, and extremes.
ISEE-3 ISEE-3, International Sun-Earth Explorer 3, was launched in 1978 to study the solar wind and Earth's magnetosphere. It was part of a trio of spacecraft, but ISEE-3 had a unique trajectory. It was the first spacecraft to be placed at a Lagrange point, a gravitationally stable spot between Earth and the Sun. From there, it monitored how solar particles and fields interact with Earth. It laid the groundwork for heliophysics. Its main objective was to study the flow of energy and plasma from the Sun to Earth. ISEE-3 measured solar wind speed, particle composition, and magnetic fluctuations. This helped explain how solar storms cause geomagnetic disturbances. The spacecraft could track solar wind changes before they reached Earth. It became a space weather sentinel.
ISEE-3 carried 13 instruments, including magnetometers, particle detectors, and plasma analyzers. It studied shock waves, turbulence, and magnetic reconnection. These processes affect not only Earth, but also other planetary environments. ISEE-3's data were critical for developing predictive space weather models. It connected solar events with terrestrial effects. In 1983, after completing its original mission, ISEE-3 was repurposed for an entirely new goal. NASA redirected it on a complex gravity assist maneuver around the Moon. This slingshot pushed it out of Earth orbit and toward the tail of a passing comet. The mission was renamed ICE, International Cometary Explorer. It became the first spacecraft to encounter a comet. On September 11, 1985, ICE passed through the tail of comet Giacobini-Zinner. It flew within 7,800 kilometers of the comet's nucleus. The spacecraft studied plasma and dust interactions in real time. It provided the first direct measurements from a cometary environment. This marked a turning point in comet science. The success of this encounter proved that deep space navigation was possible with precise maneuvers. It also demonstrated that aging spacecraft could be repurposed for new science. ICE's journey to a comet inspired later missions like Giotto, Deep Impact, and Rosetta. It showed that comets were not isolated relics, but active, dynamic bodies. After its comet mission, ICE continued to relay solar wind data from deep space. Its instruments remained functional for years beyond their expected lifespan. It provided unique observations far from Earth's magnetic influence. This allowed scientists to study the undisturbed interplanetary medium. ICE became a long-distance monitor of solar activity. In 1999, NASA officially ended communications with ICE, but in 2014, a group of citizen scientists re-established contact. They formed the ICE-3 Reboot Project and raised funds to regain control. Though its thrusters were non-functional, its instruments were still usable. It was the first time a public group took over a deep space mission. The reboot effort showed how space exploration could become more democratized. Amateur radio operators and engineers collaborated across countries. They used modern tools to control 1970s hardware. Although full navigation wasn't restored, the team recovered valuable data. It was a landmark moment in participatory science. ISEE-3's career spanned over 3 decades across 2 major missions. From Sun-Earth science to cometary exploration, it embodied adaptability. It traveled farther and did more than anyone expected. Its longevity and versatility became a model for future missions. It was a symbol of resourceful engineering. Today, ISEE-3 still orbits the Sun, silent but intact. It may be visited again one day or simply continue its eternal loop. Its instruments are off, but its legacy is active in textbooks and mission designs. ISEE-3 proved that small missions can have outsized impact. It remains one of space exploration's most underrated triumphs. Spektr-R. Spektr-R was a Russian space observatory launched in 2011 as part of the Radio Astron project. It carried a 10-meter radio telescope designed to work in tandem with ground-based arrays. This technique, called Very Long Baseline Interferometry, VLBI, creates a virtual dish the size of Earth. By combining signals from Spektr-R and terrestrial antennas, astronomers achieved record-setting resolution. The goal was to observe distant cosmic phenomena in unprecedented detail. The mission focused on radio sources like quasars, pulsars, and black holes. These objects emit low-frequency radiation that penetrates dust and gas. Spektr-R's orbit, extending nearly 350,000 kilometers from Earth, allowed enormous baseline lengths. It offered angular resolutions thousands of times sharper than Hubble in certain wavelengths. This made it ideal for probing compact and energetic objects. One of the mission's main targets was the structure of active galactic nuclei, AGN. These regions around supermassive black holes emit powerful jets of radio waves. Spektr-R helped resolve the shapes and orientations of these jets. It also studied how matter behaves near event horizons. These observations tested predictions of general relativity under extreme conditions. Spektr-R contributed to studies of gravitational lensing. It observed how massive galaxies distort the radio light of background sources. These effects revealed the distribution of dark matter in the universe. The telescope also monitored pulsar timing for search for irregularities. Subtle changes in pulse arrival times could hint at gravitational waves or exotic physics. Its ability to synchronize with radio telescopes on Earth depended on precise timing. Spektr-R used hydrogen maser clocks and ultra-stable oscillators. These kept the data streams in phase across thousands of kilometers. The mission required meticulous coordination between observatories worldwide. It was one of the most complex VLBI experiments ever conducted. The spacecraft also contributed to studies of interstellar scattering. As radio waves pass through space, they are distorted by electrons in the interstellar medium. Spektr-R helped map these distortions across different regions. This improved models of cosmic ray propagation and galactic structure. It revealed how radio signals degrade across astronomical distances. Despite technical challenges, the mission yielded hundreds of scientific publications. It strengthened global cooperation in space-based radio astronomy. Russian, European, American, and Japanese institutions collaborated in real time. Spektr-R became a symbol of what international science could achieve. It combined space engineering with planetary-scale teamwork. In 2019, contact with Spektr-R was lost due to a communications failure. Engineers attempted to re-establish control, but efforts were unsuccessful. The mission was officially declared over in the same year. Still, its scientific contributions remained active in ongoing analysis. Data from its archives continued to support research projects. Spektr-R's end highlighted the fragility of long-duration missions. Unlike telescopes in low Earth orbit, its distance complicated repairs or intervention. Yet its long-term success proved the feasibility of space-ground interferometry. It demonstrated that orbiting telescopes could extend Earth's radio vision. It paved the way for future high-orbit VLBI efforts. Plans for a successor, Spektr-Markines or Millimetron, began development during Spektr-R's operation. This new observatory aims to observe in millimeter and submillimeter wavelengths. It will probe colder cosmic regions like protostars and early galaxies. Spektr-R's legacy lives on in its scientific lineage. It set the stage for next-generation deep space radio astronomy. The mission also had pedagogical value. It trained a new generation of Russian and international astronomers in space-based VLBI. Its complex data processing pipelines advanced software techniques. It fostered expertise in timing synchronization, orbital dynamics, and signal calibration. The mission's technical innovations influenced later radio arrays. LAGEOS, Laser Geodynamics satellites, are two passive satellites launched in 1976 and 1992. Unlike most spacecraft, they carry no sensors or cameras. Instead, they're covered with retroreflectors that bounce laser beams sent from Earth. This design allows extremely precise distance measurements. The purpose? To monitor Earth's shape, rotation, and tectonic drift. Each LAGEOS satellite is a dense metallic sphere about 60 centimeters in diameter. Their compact mass helps minimize orbital perturbations. They orbit at altitudes around 5,800 kilometers, far above atmospheric drag. Their stability makes them ideal for geodetic benchmarks. Even small shifts in their paths can indicate tectonic motion below. By firing lasers from ground stations and measuring the return time, scientists calculate satellite positions within millimeters. These data reveal how continents move relative to one another. LAGEOS helped confirm the theory of plate tectonics with unprecedented accuracy. It showed that Earth's crust is in constant, measurable motion. The satellites also track polar motion and Earth's axial wobble. These subtle movements affect global positioning systems and climate models. LAGEOS provides long-term data sets to refine Earth orientation parameters. This improves navigation, satellite tracking, and timekeeping. It's one of the hidden foundations of modern geophysics. Another function is measuring Earth's gravitational field. Variations in gravity reflect mass distribution changes, from melting glaciers to shifting ocean currents. By observing LAGEOS's tiny orbital changes, scientists infer gravity anomalies. These help study sea level rise, groundwater loss, and isostatic rebound. LAGEOS became a tool for Earth system science. The satellites also help calibrate other space-based instruments. Missions like GRACE and GOES use LAGEOS data as ground truth. This ensures consistency across measurement platforms. LAGEOS anchors our understanding of global change in a physical, repeatable standard. Its value lies in its simplicity and precision. LAGEOS I and LAGEOS II continue to operate after decades in orbit. Their passive design means no batteries or fuel are needed. As long as ground lasers function, they remain usable. This longevity provides continuity across generations of research. They are quiet, reliable sentinels of Earth's subtle shifts. The satellites contributed to studies of Earth's rotational deceleration. Our planet's spin is gradually slowing due to tidal friction. LAGEOS detects this long-term trend with high fidelity. The data have implications for timekeeping and understanding Earth's interior dynamics. It links orbital mechanics to planetary evolution. LAGEOS missions are managed by NASA in collaboration with international partners. Laser ranging stations across continents contribute to the dataset. These include sites in Europe, Asia, the Americas, and Australia. The global nature of the network enhances precision and reliability. LAGEOS became a symbol of geophysical cooperation. The program's success inspired similar satellites like Aegis in Japan and LAGEOS in Italy. These newer missions extend the legacy of passive geodetic satellites. They test aspects of general relativity and monitor tectonic risk zones. LAGEOS set the standard for these precision missions. It showed how simplicity can yield profound insights. In popular culture, LAGEOS had a symbolic moment. A plaque aboard the first satellite was designed by Carl Sagan. It addressed future civilizations and noted the satellite's purpose. LAGEOS will orbit Earth for thousands of years. If discovered by distant descendants, it will serve as a time capsule of scientific thought. LAGEOS taught us how to read Earth's movements with light. Each laser pulse is a question, and the echo is data. Through it, we measure the quiet drift of continents, the flecks of ice sheets, the heartbeat of a planet. No sensors, no power, just geometry and patience. Alouette I. Launched in 1962, Alouette I was Canada's first satellite and one of the earliest space science missions. It marked Canada as the third country to design and build a satellite independently. Its primary objective was to study the ionosphere, a charged region of Earth's upper atmosphere. This layer affects radio wave propagation and global communications. Understanding it was crucial for satellite and long-distance signal reliability. Alouette I was designed by the Defense Research Telecommunications Establishment, DRTE. The satellite carried a set of instruments to probe ionospheric density, height, and composition. It transmitted radio pulses and measured their reflection from various ionospheric layers. These echoes revealed the electron distribution at different altitudes. It effectively turned the satellite into a space-based ionosonde. The spacecraft featured a long antenna system, one over 45 meters in length. This allowed it to send and receive low-frequency radio waves. Its measurements helped build vertical profiles of the ionosphere during both day and night. These data improved models for radio signal distortion. Alouette's measurements were far more consistent than ground-based observations. The mission operated in a highly elliptical orbit, reaching up to 1,000 kilometers in altitude. This gave it a broad perspective across different latitudes and geomagnetic regions. It observed how solar activity and Earth's magnetic field affected ionospheric behavior. This was especially useful during geomagnetic storms. Alouette became a crucial tool in space weather research. Its data supported the development of communication systems for aviation and defense. By revealing how the ionosphere bends and scatters signals, engineers could design more robust transmission paths. This improved reliability for radar, GPS, and early satellite communications. Alouette contributed silently but significantly to technological infrastructure. Alouette I transmitted over 1,000 hours of scientific data in its first year alone. It continued operating for a decade, well beyond expectations. During that time, it helped train scientists and engineers for future missions. Its long-term success laid the foundation for the Canadian space program. It was a technical and educational milestone. The satellite's robust design resisted harsh space conditions. It endured temperature swings, radiation, and micrometeoroid impacts. Its systems remained stable without advanced computing or automation. This resilience earned it admiration among mission designers. Alouette showed that careful engineering could achieve lasting science. The mission led directly to the development of Alouette II and the ISIS series of satellites. These expanded ionospheric studies with more instruments and longer operational ranges. Canada became known for its expertise in upper atmospheric research. Alouette sparked a national identity around scientific space exploration. Alouette also contributed to international scientific databases. Its data were shared with researchers worldwide. It became part of global efforts to understand Earth's space environment. The mission promoted peaceful collaboration during the Cold War. Its openness contrasted with the secrecy surrounding many military satellites of the era. Even after deactivation in 1972, Alouette I remained in orbit as a silent artifact. It is now considered one of the oldest intact spacecraft still circling Earth. Its orbit is expected to last for centuries. This makes it not only a scientific instrument, but also a cultural relic, a floating testament to early space exploration. In 1993, the Institute of Electrical and Electronics Engineers, IEEE, named Alouette I an IEEE milestone. It was recognized for its pioneering role in satellite engineering and ionospheric research. The satellite symbolized Canada's leap into the space age. It proved that even small nations could make big contributions. Alouette I didn't carry flashy cameras or explore distant worlds, but it revealed a critical layer of our own planet, one that shapes communication, navigation, and climate. Its legacy endures in every reliable satellite signal that passes through the sky. Quiet, technical, and transformative, Alouette was a triumph of focus and foresight.